Welcome. Tonight our journey takes us not across familiar landscapes, not through the forest where dinosaurs once shook the earth, nor across the frozen plains where mammoths wandered beneath pale skies. Tonight we go somewhere deeper, somewhere darker, somewhere far more strange. We are going beneath the waves. We are sinking slowly into the ancient oceans, into waters that existed long before any human being ever drew breath, long before there were eyes to see the sun glinting on the surface, long before there were shores as we know them. We are descending into deep time itself, into the vast, quiet alien world beneath the sea, where life first learned to move, to hunt, to see, to grow teeth, to build armor, and to become strange beyond anything we could have predicted. For more than 3 hours tonight, we will drift through over 500 million years of ocean history. We will meet creatures so bizarre that when scientists first discovered their fossils, they thought the bones had been assembled wrong. We will encounter animals with 5 eyes and grasping trunks, sharks with jaws like spiral saws, reptiles with necks longer than their entire bodies, crocodiles large enough to hunt dinosaurs, and whales with teeth the size of bowling pins. We will find worms the length of a grown man, armoured fish with jaws that could crush anything in the sea, and birds with wingspans wider than a small aircraft, their beaks lined with bony teeth that evolution reinvented from scratch. Every creature we meet tonight is real. Every fact has been checked against the fossil record and the scientific literature. None of this is myth. None of it is speculation dressed up as science. These are animals that once breathed, hunted, mated, and died in the oceans of this very planet. The same planet where you are lying right now, listening to the sound of this voice. Think of evolution not as a straight line, not as a tidy march from simple to complex, from small to large, from strange to familiar. Think of it instead as a vast and sometimes bewildering workshop, a workshop that has been running for billions of years, where nature tinkers endlessly, trying every conceivable shape, every possible jaw, every imaginable way of seeing and swimming and eating and defending. We remember the successes, the fish that became the ancestors of everything with a backbone, the reptiles that conquered the Mesozoic seas, the mammals that learned to hold their breath and dive. But what about the others, the rough drafts, the experiments that lasted for millions of years and then vanished, leaving behind only faint impressions in ancient stone? Tonight, we meet those others, the creatures that time tried to forget. So settle in now, let the familiar world fade. There is nowhere you need to be. There is nothing you need to do except breathe and listen, and let these ancient waters carry you. If you enjoy this kind of quiet exploration, take a moment to subscribe, and perhaps leave a comment telling me where you are listening from tonight and what time it is where you are. It is always wonderful to know who is joining us from around the world. Now let the lights dim. Let the hum of the modern world grow soft. Imagine the surface of the water closing gently above you, the light fading from blue to grey to black, and the silence of the deep settling around you like a blanket. We are going down. We are going back. And we are beginning our journey at the very dawn of complex animal life, in an ocean so ancient that even the continents would be unrecognizable, scattered like broken puzzle pieces across a world ruled entirely by the sea. Our first destination is the Cambrian period. Roughly 540 million years ago, give or take a few million, something extraordinary happened in the oceans of Earth. After billions of years of mostly microbial life, after endless ages of single cells and simple colonies drifting in the currents, animal life suddenly exploded into complexity. Scientists call this the Cambrian explosion, and it remains one of the most remarkable events in the entire history of life on this planet. In the span of perhaps 20 to 30 million years, which sounds like a long time but is actually a blink in geological terms, nearly every major group of animals that exist today first appeared in the fossil record. Eyes evolved, jaws appeared, shells hardened, claws sharpened, predators and prey began their ancient endless dance. The ocean, which had been a quiet place of drifting microbes and soft mats of algae, suddenly teemed with creatures of astonishing variety and strangeness. The continents during this time were unrecognizable. There was no North America, no Europe, no Asia as we know them. Instead, scattered fragments of land drifted across the face of a world dominated by warm, shallow seas. And it is in the sediments of those seas, particularly in a place called the Burgess Shale, high in the Canadian Rockies of British Columbia, that some of the most extraordinary fossils from this period have been preserved. The Burgess Shale is a window into the Cambrian Ocean, a snapshot of life taken over 500 million years ago, capturing creatures so strange that they challenged everything scientists thought they knew about the history of animal life. And it is here, drifting perhaps just above the silty floor of that ancient Cambrian sea, that we meet our first creature tonight. One so baffling, so utterly unlike anything alive today, that when the scientist who first reconstructed it presented his findings at a conference, the audience reportedly laughed. This is Opabinia regalis. Even the name carries a hint of the exotic, the unfamiliar. Opabinia was a small creature, only about 4 to 7 centimeters long, roughly the size of a large shrimp. You could have held it comfortably in the palm of your hand, though you might not have wanted to. Its body was soft and segmented, without any hard shell or exoskeleton. Along its sides extended a series of lobe-like flaps, overlapping gently, which likely undulated in slow, rhythmic waves, propelling the creature through the water with a kind of graceful rippling motion. At its rear, a fan-shaped tail, possibly composed of 3 pairs of upward-pointing flaps, helped with steering and stability as it cruised just above the muddy seabed. So far perhaps you might imagine something vaguely like a primitive shrimp or a strange worm. But then we arrive at the head, and this is where Opabinia departs entirely from anything familiar. Mounted on the front of its head were not 2 eyes as we might expect, not even 4. Opabinia had 5 eyes, 5 separate individual eyes, each perched on its own short stalk, arranged across the top of its head. Imagine those 5 stalked eyes swiveling independently, scanning the murky Cambrian waters in almost every direction simultaneously. It would have had something approaching panoramic vision, able to watch for prey below, predators above, and movement on all sides, all at the same time. In a world where most creatures had simple light-sensing patches, Opabinia's 5-eyed surveillance system was something extraordinary. But the eyes were not even the strangest thing about this creature. Extending forward from beneath those 5 stalked eyes was a long, flexible proboscis, a trunk of sorts segmented and hollow, almost like a tiny vacuum cleaner hose or the snout of some impossible miniature elephant. This proboscis was perhaps as long as a third of the creature's entire body, and it was clearly highly mobile, capable of twisting and turning and reaching far ahead. And at its very tip, this trunk ended not in nostrils, not in a simple opening, but in a small, menacing, grasping claw, armed with prominent spines. Picture the feeding process. Opabinia drifts slowly above the Cambrian seafloor, its 5 eyes scanning the mud below. It spots something, perhaps a small soft-bodied worm or a tiny invertebrate trying to hide in the sediment. The long proboscis snakes downward. The claw at its tip opens, seizes the unfortunate prey with its spines, and then retracts, curling back toward the creature's body. And here is another strange detail. The mouth of Opabinia was not at the front of its head, where we would expect it. The mouth was located underneath, facing backward, positioned so that the proboscis could deliver food directly to it from below. It was a feeding mechanism unlike anything else known, before or since. A remote-controlled hunting arm paired with a 5-eyed wide-angle surveillance system. The paleontologist Harry Whittington spent years carefully preparing and studying the Opabinia fossils from the Burgess Shale. When he presented his reconstruction in the 1970s, the sheer strangeness of the creature, with its 5 eyes and its clawed trunk, reportedly drew laughter from the assembled scientists. It was simply too bizarre, too alien, too far removed from anything in their experience of animal life. And yet the fossils were clear. Opabinia was real. It appears to have been a relatively rare inhabitant of its ecosystem. Its fossils are far less common than those of trilobites or other arthropods found in the same deposits. Perhaps it was a specialized predator occupying a narrow ecological niche. Perhaps its soft body simply did not preserve as readily as the hard shells of its neighbours. We may never know for certain. What we do know is that Opabinia represents a body plan, a way of being alive that ultimately led nowhere. There are no five-eyed, trunk-clawed creatures swimming in our oceans today. This was an experiment, a beautiful and baffling one that evolution tried and then abandoned. It challenges our deepest assumptions about what animals should look like. It reminds us that the forms life takes are not preordained, not necessarily steps on a ladder leading toward us, toward familiarity. Sometimes evolution simply tries something wonderfully, profoundly strange. To contemplate Opabinia is to glimpse the sheer, unbridled, almost alien creativity of life's earliest chapters, a time when the rules were still being written and almost anything seemed possible. A five-eyed phantom drifting silently through the dawn of animal life. From the same ancient seabed, from the same extraordinary window into the Cambrian explosion preserved in the Burgess Shale, comes another creature so bizarre, so difficult to interpret, that its very name reflects the profound confusion it inspired. Hallucigenia. If Opabinia was baffling, Hallucigenia seemed, for a time, to defy biological logic altogether. The name was chosen deliberately. It comes from the word hallucination, because this tiny creature, perhaps only 1 to 3 centimeters long, looked like something conjured from a fever dream rather than assembled by the careful hand of natural selection. When the paleontologist Simon Conway Morris first described Hallucigenia in detail in the 1970s, he and his colleagues struggled immensely to make sense of the fossilized remains. The specimens from the Burgess Shale were small, faint impressions in ancient rock, and the anatomy was so unfamiliar that even determining which end was the head and which was the tail proved enormously difficult. The initial reconstruction depicted something almost impossible, a creature that appeared to walk along the seafloor on pairs of stiff, sharp spines, like a tiny animal tottering on rigid stilts. Arching above its long, tubular body was a row of soft, waving tentacles, reaching upward into the water, interpreted perhaps as feeding appendages. It was a reconstruction that looked magnificent and otherworldly, but it presented profound biological problems. How could an animal walk effectively on rigid spikes? What exactly were those waving dorsal tentacles doing? The creature seemed almost deliberately nonsensical, as if evolution had assembled it as a joke. But the story of Hallucigenia is also a wonderful story of how science works, of how new evidence and new ways of looking can radically change our understanding. In the 1990s and 2000s, new fossil discoveries from sites in China, particularly the Chengjiang biota in Yunnan province, preserve specimens of related creatures with far greater detail than the Burgess Shale originals. Armed with these new fossils and with powerful electron microscopes that could reveal structures invisible to the naked eye, scientists re-examined the evidence, and they discovered the truth. The paleontologists had reconstructed Hallucigenia upside down. Those stiff spines were not legs at all. They were defensive armour, pointing upward from the creature's back, a formidable row of sharp mineralized stakes designed to deter any predator that might try to bite into it from above. And those waving tentacles, the supposed feeding appendages reaching up into the water, they were the real legs, pairs of soft, flexible, clawed appendages called lobopods, extending downward from the tubular body, carrying the creature slowly and carefully across the muddy Cambrian seafloor. Even the head had been misidentified. For years, a rounded dark blob at one end of the fossil was assumed to be the head. But closer examination, using scanning electron microscopes on the beautifully preserved Chinese specimens, revealed that this blob was not a head at all. It was likely just decay fluids, or gut contents that had been squeezed out of the body during the fossilization process. The actual head was at the other end, a small, subtle structure equipped with simple eyes and a tiny mouth that led to a gut running the full length of the body. So the modern picture of hallucigenia finally came into focus. A small, worm-like creature, perhaps related to modern velvet worms, those soft-bodied animals found in tropical forests today, and possibly also to the tardigrades, the nearly indestructible water bears that can survive in outer space. Hallucigenia belonged to an ancient group of animals called lobopodians, creatures that walked on multiple pairs of soft, stubby legs. Imagine this tiny creature now, moving deliberately across the Cambrian mud. Its body is soft, tubular, vulnerable, but rising from its back is a fearsome row of tall, sharp, mineralized spines, like a forest of tiny swords. Any predator attempting to bite down on hallucigenia from above would find its mouth pierced by those rigid stakes. It was a creature built for passive defense, a living pincushion navigating a dangerous world where the first great predators were just beginning to evolve. Its movements were likely slow and cautious. Its small head probed the sediment, perhaps searching for particles of food, organic debris, or bacterial mats growing on the ocean floor. It was not a hunter. It was a scavenger, a browser, a tiny armoured wanderer in a world that was becoming increasingly hostile. Even with the corrected reconstruction, hallucigenia remains wonderfully strange. Its combination of soft, flexible legs and rigid, sharp dorsal spines is essentially unique. Its exact position in the great family tree of life is still debated among scientists. Some place it firmly with the velvet worms. Others argue for a more distant relationship. It represents yet another Cambrian experiment, a creature exploring the possibilities of soft bodies combined with hard defences, of walking on numerous small limbs while presenting a prickly exterior to the world. Like Opapinia, its specific body plan appears to have been an evolutionary dead end. No direct descendants of hallucigenia walk the earth or swim the seas today. Its lineage, whatever it was, eventually faded away, but its story endures. Hallucigenia is a reminder of the challenges of reading the deep past from fragmentary evidence. It shows how our initial perceptions can be profoundly wrong, how even the most careful scientist can look at a fossil and see it the wrong way around. And it underscores the sheer, almost playful, creativity of early animal evolution. A time when life was trying out every imaginable combination of spikes, legs, eyes, and mouths, filling the ancient seas with creatures that continue to inspire wonder, confusion, and a deep appreciation for the strange and ancient history of life on Earth. A spiky phantom, finally walking right side up through the Cambrian dawn, lurking in the same ancient Cambrian waters as the five-eyed Opapinia and the spiky upside-down hallucigenia, was another creature entirely, vastly larger, undeniably predatory, and initially just as baffling to the scientists who unearthed its scattered remains. This was Anomalocaris, the abnormal shrimp, a name that hints at a deeply confusing discovery, but utterly fails to capture the bizarre majesty and the lightly terror that this giant of the early seas inspired in everything around it. For many years, Anomalocaris was not recognized as a single creature at all. Its body parts, discovered separately in the Burgess Shale and in other Cambrian fossil sites scattered around the world from Canada to China to Australia, were so unlike anything known that they were classified as entirely different organisms. Imagine the confusion. Paleontologists find strange circular fossilized structures resembling pineapple rings or sliced fruit, with a complex tooth-lined opening in the centre. They classify these as a type of fossil jellyfish and give them the name Patia. Elsewhere, they discover spiky segmented appendages that look somewhat like the dismembered body of a shrimp or some unknown arthropod. These are named Anomoa, and Amalocaris, the abnormal shrimp, and scattered among these finds are large flattened lobed bodies without any obvious limbs or head, sometimes interpreted as a type of sea cucumber or some other soft-bodied enigma. 3 separate creatures classified into 3 separate groups, sitting in museum drawers around the world. It took decades of painstaking work, the discovery of more complete specimens, and a brilliant feat of paleontological detective work in the early 1980s by Harry Whittington, Derek Briggs, and Simon Conway Morris to finally piece the puzzle together. The jellyfish was not a jellyfish. It was the mouth. The abnormal shrimp was not a whole shrimp. It was one of a pair of large, spiny, grasping appendages attached to the front of the head, and the sea cucumber body was the main torso of the animal to which all these parts belonged. Suddenly, from these scattered, misunderstood fragments, a complete and truly extraordinary animal emerged. An Amalocaris was revealed not as a collection of separate oddities, but as a single large, highly sophisticated predator unlike anything else in the Cambrian seas. Let us try to picture it now, perhaps gliding through the water column, its immense eyes scanning the depths below. By Cambrian standards, Anomalocaris was a giant. Some species, like Anomalocaris canadensis, may have reached lengths of up to a metre, perhaps even more, making it one of the largest animals on the planet at that time. In a world where most creatures measured just a few centimetres, Anomalocaris was a colossus. His body was streamlined and elegant, flanked by a series of flexible lobes or fins running along each side. These lightly undulated in waves, propelling the creature smoothly and perhaps surprisingly quickly through the water. Imagine a giant swimming centipede, or a fleshy cuttlefish, rippling along with a strange and graceful efficiency. At the rear, a fan-like tail structure provided stability and steering. At the front was a distinct head, dominated by 2 remarkable features. First, a pair of large, complex, compound eyes mounted on stalks. These eyes were incredibly advanced for their time, possessing perhaps 16,000 individual lenses each, granting Anomalocaris exceptionally sharp vision, far superior to the simple light-sensing organs of most of its contemporaries. Imagine those huge, multifaceted eyes swiveling, scanning the environment with an acuity that was previously unknown in the history of life on Earth. And extending forward from beneath these eyes were those 2 formidable, grasping appendages, the original abnormal shrimp. These segmented arms were lined with sharp spines, acting like fearsome grappling hooks, perfectly designed for seizing prey. They were likely strong and flexible, capable of snatching trilobites off the seabed or capturing other creatures swimming through the water column. Between these arms, on the underside of the head, was that circular mouth, the fossilized pineapple slice that had once been called Patia. It was a ring of hard plates surrounding a central opening lined with sharp inward-pointing teeth or spines. This structure likely did not function like a crushing jaw, but perhaps more like a grasping, squeezing apparatus, capable of holding prey firmly, while perhaps cracking softer shells or sucking out soft tissue. Put together, Anomalocaris was a masterpiece of Cambrian engineering. It possessed the size, the speed, the incredible vision, and the specialized weaponry to dominate the food web of its time. It was arguably the first large, actively swimming predator in the history of life on Earth. Its presence in those ancient oceans would have exerted immense evolutionary pressure on everything around it. Trilobites, those ubiquitous armoured creatures of the Cambrian, have been found with bite marks and healed injuries that match the mouth of Anomalocaris. Some scientists believe that the very evolution of hard shells, of armour, of defensive spines and burrowing behaviour in Cambrian animals was driven in part by the need to escape predators like this one. Anomalocaris and its relatives, collectively known as the radiodonts, were widespread and clearly successful. Their fossils have been found on multiple continents, indicating they dominated the oceans for tens of millions of years, and yet, like so many Cambrian experiments, Their specific lineage eventually died out, leaving no direct descendants in the modern world. They were a unique solution to the challenges of predation in those early seas, and when conditions changed, their solution no longer worked. To contemplate an Amalakaris is to witness the dawn of active predation on a grand scale. It is to see evolution equipping a creature with the tools for pursuit, capture and consumption in ways never before attempted. A beautiful, terrifying, and utterly alien glimpse into the world just after the invention of animals. The abnormal shrimp was, in truth, the Cambrian's first super-predator. We linger now in the Cambrian seas, but we turn our attention from the large and terrifying to the impossibly small, because not all of the ocean's strangest creatures were built on a grand scale. Some of the most bizarre animals that ever lived were so tiny that you would need a microscope to see them at all. Meet Saccharhitis coronarius, a creature so small, so simple, and yet so profoundly strange that it reshaped our understanding of the very earliest chapters of animal evolution. Saccharhitis was discovered not in a dramatic cliff face or a windswept mountainside, but in microfossils, tiny grains of ancient sediment from Shanxi province in central China. The fossils date to roughly 540 million years ago, placing Saccharhitis at the very beginning of the Cambrian period, right at the threshold of the explosion of complex animal life. And the creature preserved within those grains of stone is almost comically simple. Imagine a wrinkly, bag-shaped body, a sac, roughly 1 millimeter across, barely visible to the naked eye. The most prominent feature of this tiny sac is its mouth, which is enormous relative to the rest of its body. A wide, gaping, circular opening surrounded by folds and wrinkles of tissue. The mouth dominates the entire front end of the creature, and around the body, scattered across its wrinkled surface, are several small, cone-shaped openings, perhaps 8 or 9 of them, which may have served as primitive gill-like structures, allowing water to pass through the body after food was extracted. And here is perhaps the most remarkable detail. Saccharhitis appears to have had no anus, no separate exit for waste. The prevailing interpretation is that whatever Saccharhitis ate went in through that giant mouth, and whatever was left after digestion came back out the same way. A creature that is, in essence, a mouth with a body attached, a wrinkly sac that eats and expels from the same opening. When Saccharhitis was first described in 2017 by a team of researchers led by Jian Han, it was proposed as possibly the earliest known deuterostom. This is significant because deuterostomes are the great branch of the animal family tree that includes all vertebrates, which means fish, amphibians, reptiles, birds and mammals, including us. If this interpretation were correct, then this tiny, wrinkly, anusless sac might be among the most ancient ancestors of every creature with a backbone, the great-great-grandparent, trillions of generations removed, of whales and sharks and seahorses and you and me. However, science is a process of constant refinement. In 2022, a follow-up study led by Yunhuan Liu, published in the journal Nature, re-examined the evidence and concluded that those cone-shaped openings around the body were not gull pores at all, but the broken bases of spines. This reclassification placed Saccharhitis not among the deuterostomes, but among the ecdysozoans, the great group that includes insects, crustaceans, and roundworms. The debate about exactly where this creature belongs on the tree of life continues, but regardless of its precise classification, Saccharhitis remains a profoundly strange and thought-provoking animal, a creature from the very dawn of complex life, so simple that it is essentially just a mouth and a body, filtering the ancient mud of the Cambrian seafloor. It reminds us that the grand pageant of animal evolution began not with monsters and giants, but with creatures so small and so simple that they would be invisible to us if we stood beside the shore of that ancient ocean. The ocean's smallest strange resident, a wrinkly sac, drifting through the dawn of everything. We return now to creatures of more impressive proportions, Still in the Cambrian, still in the Burgess Shale region, but now we meet an animal that represents the apex of Cambrian body armour, a creature whose head was so large, so strangely shaped, that it accounted for nearly 2/3 of its entire body length. This is Titanochorus guineysi, the Titan helmet. Titanochorus was announced to the world in 2021 by paleontologists Jean-Bernard Caron and Joe Moisiuk of the Royal Ontario Museum. It was found in the Burgess Shale deposits of Kootenay National Park in the Canadian Rockies, and when Caron first described it to the press, he called it the large car of the Cambrian period, because it was one of the biggest animals in its ecosystem, and it essentially drove across the ocean floor like a vehicle. At roughly 50 centimetres long, about 1.5 feet, Titanochorus may not sound enormous by modern standards, but in the Cambrian world, where most animals measured just a few centimetres, 1/2 metre made you a giant. And it was not just the size but the shape that was so extraordinary. The defining feature of Titanochorus was its massive head carapace, a broad, flattened, helmet-shaped shell that extended far beyond its body, covering the creature like an oversized visor. This single structure accounted for perhaps 2/3 of the animal's total length, making it appear almost all head and no body. Imagine a living dinner plate with legs underneath, or a biological Roomba sweeping across the ocean floor. Beneath this enormous helmet, on the underside facing the seafloor, Titanochorus possessed a pair of raking appendages, smaller and less dramatic than the grasping arms of Anomalocaris, but clearly functional. Behind these appendages was a circular mouth lined with tooth-like structures, very similar in design to the mouth of its larger relative. Titanochorus belongs to the radiodonts, the same group as Anomalocaris, but it occupied a completely different ecological niche. While Anomalocaris was a free-swimming pursuit predator, Titanochorus was a bottom feeder. Imagine it moving slowly, deliberately, across the Cambrian seafloor, that immense helmet-shaped carapace acting almost like a plough. It lightly disturbed the sediment as it moved, using its raking appendages to sift through the mud and draw small prey, items toward its waiting mouth. Tiny worms, soft-bodied larvae, organic particles, the fine debris of life and death that accumulates on any ocean floor. All of it would have been swept into the path of this biological harvesting machine. The helmet itself may have served multiple purposes. It clearly provided protection, forming a hard, broad shield against predators attacking from above. But it may also have acted as a hydrodynamic tool, helping the creature maintain its position on the seafloor in currents, or perhaps directing water flow across its feeding appendages. Some scientists have even speculated that it might have been used to plough into soft sediment, flushing out hidden prey. Titanochorus is a reminder that even in the earliest days of complex animal life, the ocean floor had its own specialists. Not every successful creature was a fast swimmer or a fearsome predator with sharp claws and keen eyes. Some of the most effective organisms were the slow, methodical ones, the ones that found their living in the quiet mud below, sweeping up what others left behind. The Cambrian was not just a world of dramatic hunters like Anomalocaris. It was also a world of patient armoured bulldozers like Titanochorus, quietly dominating the benthic zone with their absurdly oversized heads. A helmeted giant, wider than it was long, slowly ploughing through the ancient mud. Another strange and wonderful product of evolution's wildest experimental phase. We leave the Cambrian now. Let the waters around you shift. Let the light change. We are moving forward through an immense gulf of time. Tens of millions of years pass like the slow turning of a page. The Cambrian fades, and the oceans that replace it are different. More complex, more dangerous, more recognizable perhaps, but still profoundly alien by our standards. We are entering the Ordovician, and then the Silurian, then the Great Devonian period, the Age of Fishes. Life in the seas has not merely continued, it has intensified. The first vertebrates, creatures with the beginnings of backbones, have appeared and diversified. Jaws have evolved, and with jaws came a new kind of predation, more powerful and more efficient than anything the Cambrian could muster. The arms race between predator and prey that began with Anomalocaris has escalated dramatically. Armour has thickened, teeth have sharpened, eyes have grown keener. The ocean has become a battlefield, and the creatures that inhabit it are increasingly formidable. The ancient seafloor is still populated by trilobites, though their golden age is slowly waning. Crinoids, the sea lilies, form delicate underwater gardens. Brachiopods, the lamp shells, pave the bottom in dense colonies. Corals are building the first great reefs, and swimming above all of this, in the open water column, are creatures of increasing size and sophistication. It is here, in these Paleozoic seas that stretch from roughly 480 to 360 million years ago, that we will meet our next group of strange and wonderful inhabitants. Giants and monsters of the ancient deep, creatures that ruled the oceans long before the first dinosaur ever walked the earth. Our attention turns first to the Ordovician and Silurian periods, roughly 480 to 420 million years ago. The shallow seas of this time are vast and warm, stretching across much of the planet's surface. There are no forests on land, no grasses, no flowers. The continents are mostly barren rock and thin crusts of microbial life. The real action, the real complexity, the real drama of life on Earth at this moment is happening entirely beneath the waves. And ruling over these ancient oceans, cruising slowly through the water column like living torpedoes, were creatures of immense size and simple brutal geometry, the giant orthoconic nautiloids. The word orthocone simply means straight cone, and it refers to a variety of ancient straight-shelled cephalopods. These were relatives of the modern nautilus, the graceful spiral-shelled creature that still lives in the deep waters of the Pacific today. But while the nautilus coils its shell into a beautiful compact spiral, the orthocones wore their shell stretched out straight. Imagine a single long, gently tapering cone of calcium carbonate, like a colossal ice cream cone, stretching for meters through the water. Among the largest of these were creatures belonging to genera, like Indoceras and Camaraceras, and the sizes they achieved are staggering, based on fossilized fragments of their enormous shells, while complete specimens are exceedingly rare. Estimates for the largest individuals reach lengths of 6, 9, perhaps even close to 10 meters. That is 30 feet or more of straight-shelled cephalopod drifting through the Ordovician Ocean. This places them among the largest animals on Earth during the early Paleozoic, undisputed apex predators of their time, ruling the seas for tens of millions of years before the evolution of jawed fish would challenge their dominance. The shell of an orthocone was not solid. Like the later Nautilus and the Ammonites, it was divided internally into a series of chambers by thin walls called septa. The living animal, a creature that likely resembled a large squid or octopus, with tentacles, a sharp parrot-like beak, and sophisticated eyes, occupied only the final, largest chamber at the open end of the cone. The preceding chambers were filled primarily with gas, connected by a tube of living tissue called the siphuncle. By carefully regulating the amount of gas and liquid within these chambers, the orthocone could precisely control its buoyancy, allowing it to hang effortlessly at any desired depth in the water column. Like a perfectly balanced submarine, it did not need to constantly swim to avoid sinking. It could simply float, neutrally buoyant, waiting. How did it move? At the open end of the shell, surrounding the head and tentacles, was likely a funnel-like structure called the hypernome. By forcefully expelling water through this funnel, the orthocone could achieve jet propulsion, moving backward through the water with the large, heavy shell trailing behind its soft body. This was probably not a system built for sustained high speed, but rather for deliberate, controlled movements, for adjusting position, for short bursts of acceleration to ambush prey or to escape from one of the few creatures large enough to threaten it. Imagine the perspective of a trilobite, scuttling across the Ordovician seafloor. A vast shadow falls from above. Looking up, it sees the immense, tapering cone of an Endocerus hanging silently, almost motionless in the water column far overhead. Then, perhaps triggered by movement or the chemical scent of prey, the creature stirs. A cloud of water jets from its funnel. Tentacles, perhaps 10 or more of them, unfurl from the opening of the shell, reaching downward. A sharp parrot-like beak snaps open and shut. For the trilobite, or for any early jawless fish, any sea scorpion swimming nearby, this descent would be inescapable. These giant orthocones represent a different kind of marine dominance from anything we have seen before. Not the agile speed of a fish, nor the crushing power of a jaw, but the slow, patient, inescapable presence of a living fortress, a buoyant castle armed with grasping tentacles and a slicing beak. They were the undisputed rulers of the Ordovician and Silurian seas, and their fossils, particularly the long-chambered shells often preserved as internal moulds, are found in marine rocks of this age worldwide. Like so many creatures in our story, the giant orthocones eventually declined, perhaps facing competition from the evolving jawed fish, or succumbing to environmental changes like the devastating late Ordovician glaciation. Their straight-shelled body plan gave way to the more compact, perhaps more maneuverable, coiled shells of the ammonites and later nautiloids. But for tens of millions of years they were the kings of the ancient seas, immense cones drifting through the water, embodying the simple, profound, and utterly alien strangeness of life in the deep Paleozoic. Sharing these same Paleozoic waters, and persisting for an even longer stretch of geological time, was another group of creatures that inspire a particular kind of primal unease. They looked, in many ways, like something from a nightmare. Giant arthropods, armoured and segmented, with compound eyes, grasping claws, and in some cases, bodies longer than an adult human being. These were the Eurypterids, the sea scorpions. The name sea scorpion is somewhat misleading. Eurypterids were not true scorpions, though they were related to them, belonging to the broader group of eulypterids that also include spiders, ticks, and horseshoe crabs. But the resemblance to scorpions was close enough to earn them the nickname, and it is an evocative one. Imagine a scorpion scaled up to enormous size and set loose in the ocean, and you begin to approach the reality of what these creatures were. Eurypterids first appeared in the Ordovician period, roughly 470 million years ago, and they persisted all the way through to the end of the Permian, about 252 million years ago, when the Great Dying, the worst mass extinction in Earth's history, finally wiped them out. That is a reign of over 200 million years, an astonishing duration that speaks to the fundamental success of their body plan. Most Eurypterids were relatively modest in size, comparable to modern horseshoe crabs. But some species grew to truly extraordinary proportions. The largest known Eurypterid, Echolopterus renanii, from the Devonian of Germany, is estimated to have reached lengths of 2.5 meters, over 8 feet. This makes it the largest arthropod ever known to have lived, larger even than the giant carboniferous millipede Arthropleura that we might encounter in other stories. A sea scorpion as long as a tall man and considerably heavier. The body of a Eurypterid was divided into a head shield bearing compound eyes and a set of appendages, a segmented middle section, and a tail that in some species ended in a sharp spine or a flattened paddle. The appendages varied considerably between species, reflecting different lifestyles and diets. Some had large, powerful chelicerae, the pincer-like claws at the front of the head, clearly designed for seizing and holding prey. Others had smaller, more delicate appendages suited for sifting through sediment. Many possessed paddle-like rear limbs that made them strong, capable swimmers. Eurypterids inhabited a wide range of aquatic environments. Some were fully marine, cruising the open oceans. Others lived in brackish water, in the estuaries and lagoons where fresh water meets the sea, and some species appear to have been primarily freshwater dwellers, inhabiting the rivers and lakes of the ancient world. This versatility is another key to their long success. Imagine encountering one of the larger species in the shallows of a Silurian lagoon. The water is warm and murky. You see a dark shape on the sandy bottom, perhaps 1.5 meters long, its segmented body gleaming faintly in the dim light. Its compound eyes, fixed in its broad head shield, seem to be watching you. Its front appendages, tipped with sharp, grasping claws, are held slightly forward, ready. It is not moving. It is waiting. Then, with a sudden, powerful sweep of its rear paddles, it surges forward, a blur of chitin and intention. The sea scorpions were a crucial part of Paleozoic marine ecosystems for an almost inconceivable stretch of time. They witnessed the rise and fall of the trilobites. They saw the first fish evolve jaws. They were there when the first vertebrates crawled onto land. And they endured through multiple mass extinctions before the Permian catastrophe finally ended their story. They are another reminder that the oceans of the deep past were ruled by creatures profoundly different from anything alive today. A world where arthropods, not fish, not reptiles, not mammals, could grow to the size of a human being and dominate the food web of an entire ocean. We move now into the late Devonian period, roughly 380 to 360 million years ago, and we encounter what may be the single most terrifying fish that ever lived. Not the most famous, perhaps. That title probably belongs to Megalodon, whom we will meet later in our journey. But for sheer, brutal, bone-crushing power, for the combination of impenetrable armour and devastating weaponry, nothing in the history of the oceans quite compares to Dunkleosteus. Dunkleosteus was a placoderm, a member of an extinct group of fish called the plate-skinned fish. Forget sleek scales and flexible bodies. Dunkleosteus was a living tank, a biological battleship. The front third of its body, including its massive head, was encased in thick interlocking plates of solid bone, forming an impenetrable suit of armour. Behind this armoured head, the body tapered into a more conventional, presumably muscular trunk and tail, though the rear portions are known only from rare and fragmentary impressions. The size of Dunkleosteus is difficult to overstate, while exact dimensions are debated, because most fossils consist only of the armoured head shield and jaw plates. Conservative estimates place the largest individuals at around 6 meters long, roughly 20 feet, and weighing well over a metric ton. Some reconstructions suggest even larger sizes, potentially approaching 8 or 9 meters. In the Devonian Ocean, this made Dunkleosteus one of the largest vertebrate predators the planet had ever seen. But it was not just the size or the armour that made this creature so formidable, it was the mouth. Dunkleosteus had no teeth, not in the conventional sense. Instead, the edges of its powerful jaws were formed from exposed sharpened plates of bone, extensions of the cranial armour itself. These bony plates functioned as self-sharpening guillotine blades. As the upper and lower jaw plates slid against each other during the act of biting, they honed themselves, maintaining a cutting edge that could slice through almost anything. The front plates formed pointed fang-like projections for piercing and gripping prey, while the side plates acted like shears, capable of cutting through flesh, bone, and even the armour of other placoderms. Biomechanical studies, particularly the groundbreaking work by Philip Anderson and Mark Westneat, published in 2007, have calculated the bite force of Dunkleosteus, and the numbers are almost unbelievable. The estimated bite force rivals that of Tyrannosaurus rex and the giant shark Megalodon. It possessed one of the most powerful bites of any creature that has ever lived. And there is more. The unique hinge skull of Dunkleosteus allowed it to open its mouth with incredible speed, perhaps in less than 1/50th of a second. This rapid gape created a powerful suction force, drawing water and unfortunate prey directly into the path of those devastating bony blades. Then the jaws snapped shut with crushing, shearing force. What did this armoured behemoth eat? The answer is almost certainly anything it wanted. Fossil evidence, including partially digested fish remains found associated with Dunkleosteus armour, confirms that it was an active and successful predator. It likely preyed upon large fish, including the early sharks that shared its waters. It hunted other, smaller placoderms, cracking their armour with those self-sharpening jaws. Ammonites, crustaceans, and perhaps even the first large amphibians venturing near the water would have been vulnerable. Dunkleosteus represents the peak of placoderm evolution. These armoured fish dominated the world's oceans for tens of millions of years during the Devonian, a period sometimes called the Age of Fishes, precisely because of the incredible diversity and success of fish during this time. Yet despite their reign, the placoderms vanished entirely at the end of the Devonian, victims perhaps of changing ocean conditions, the rise of the first great shark lineages, or some combination of factors we do not fully understand. They left no direct descendants. To contemplate Dunkleosteus is to witness a different kind of predatory perfection. Not the sleek speed of a shark, but the brutal, inexorable power of an armoured battering ram equipped with bone-shearing blades, a creature born of a world where defence, in the form of heavy plating, was paramount, and defence evolved in terrifying lockstep. A true monster from the Age of Fishes. Before we leave the Devonian behind, there is one more creature lurking in these ancient seas that deserves our attention. Not a fish, not a cephalopod, not an arthropod in the conventional sense, but something far more humble and yet, in its own way, equally unsettling. Websteroporion armstrongi, a worm. The name might sound familiar to fans of a certain genre of music, because Websteroporion was named in honour of Alex Webster, the bassist of the death metal band Cannibal Corpse. The researchers who described this creature, led by Mats Eriksson of Lund University, and published in the journal Scientific Reports in 2017, were clearly struck by its ferocity and thought the name fitting. Websteroporion was a polychaete worm, a marine bristle worm, the kind of segmented, soft-bodied creature that still inhabits ocean floors around the world today. Modern polychaetes are common and often small, typically measuring just a few centimetres. Some are predators, some are filter feeders, some burrow in the sediment. But Websteroporion was not small. Based on the size of its fossilised jaws, which were over 1 centimetre long, and are the largest marine worm jaws ever found in the fossil record, scientists estimate that this creature reached a total body length of up to 2 metres, 6.5 feet of worm, the largest marine-jawed worm ever recorded. The fossils were found in Devonian rocks from Ontario, Canada, roughly 400 million years old. Like most polychaete worms, its soft body did not preserve well. What did survive were those remarkable jaws, hard, sharp, and clearly built for a predatory lifestyle. Modern polychaete worms with similar jaw structures are active hunters, seizing smaller creatures with their eversible jaws, which they can thrust outward from their bodies like a sudden snapping trap. Imagine this creature on the Devonian seafloor. 2 metres of segmented muscular worm, moving through the sediment, or perhaps ambushing from a burrow. Its head appears. The jaws avert, snapping outward like a spring-loaded mechanism, seizing a smaller worm or crustacean with sharp-toothed mandibles before retreating back into the safety of its tunnel. Websteroporion is a reminder that the strangeness of the ancient oceans was not confined to the large and dramatic. Even the worms, those most humble of creatures, achieve proportions in the deep past that seem almost impossible by today's standards. The ocean floor of the Devonian was not a quiet, empty place. It was home to giants of all kinds, including giant worms with jaws that earned them a death metal tribute. We leave the Devonian now, with its armoured fish and its giant worms, and we drift forward through time once more. The ocean around us changes. The great placoderms vanish, victims of an extinction event at the end of the Devonian that reshuffled the marine world. Sharks, true sharks with cartilaginous skeletons and rows of replaceable teeth, begin their long ascent. Bony fish diversify and spread. On land, the first forests are growing. The first amphibians are exploring the margins of rivers and swamps. The continents are slowly coming together, assembling into the supercontinent Pangaea, and the oceans surrounding this vast landmass are changing in response. We are entering the Carboniferous and Permian periods, a span of time from roughly 360 to 250 million years ago. The oceans of this era are warmer, shallower in many places, and they harbour creatures whose fossils would puzzle and astonish scientists for over a century after their discovery. The first of these is a shark, or rather, a shark-like fish, because the precise classification of this creature has been debated for as long as its fossils have been known. What is not debated is the utter strangeness of its most famous feature, a feature so bizarre that it took more than 100 years of scientific investigation to figure out where on the animal's body it actually belonged. This is Helicoprion, the spiral saw. The story of Helicoprion begins not with a complete fossil, because its cartilaginous body, like that of modern sharks and rays, almost never preserved. Instead, what paleontologists have been finding since the late 1800s are strange, coiled whorls of fossilized teeth. Imagine a perfectly symmetrical spiral, like a tightly wound watch spring or a circular saw blade, composed entirely of sharp triangular teeth, getting progressively larger toward the outer edge, all fused together at their bases into a single continuous curving structure. These tooth whorls are often beautiful in their geometric precision, and they are found in Permian marine rocks around the world, from Western Australia to Norway to Idaho. But what kind of creature could possibly possess such a thing? And more bafflingly, where on its body did this extraordinary structure belong? For over a century, scientists proposed wildly different reconstructions. Some imagined the spiral sitting on the creature's snout, coiling outward like a bizarre horn. Others placed it on the tail fin, a strange serrated weapon trailing behind the animal as it swam. A few even suggested it sat atop the dorsal fin, a spinning crest that defied all functional logic. The most common early hypothesis placed the whorl in the lower jaw, curling downward and outward like an external buzzsaw, perhaps used to slash at schools of fish or to cut into the shells of ammonites. For decades, the image of Helicoprion with an external saw blade curling from its chin became iconic, appearing in countless books and illustrations. But none of these reconstructions were entirely convincing. How could an animal effectively hunt, or even swim normally, with such an awkward external spiral of teeth? The breakthrough came in the 2010 era, when advanced imaging technologies, particularly CT scanning, were applied to exceptionally well-preserved specimens, where the tooth whorl was found associated with faint remnants of the surrounding jaw cartilage. A landmark study led by Leif Tapanala at Idaho State University, published in 2013, finally revealed the astonishing truth. The tooth whorl belonged entirely inside the mouth. Specifically, it was embedded within the lower jaw. It was not an external weapon, but an internal, continuously growing conveyor belt of teeth. Here is how it worked. Within the lower jaw, at the symphysis, the point where the two halves of the jaw meet at the front, teeth grew continuously throughout the animal's life. But unlike most sharks, which shed old teeth as new ones push forward, Helicoprion's teeth remained fused together at their roots. As new, larger teeth formed at the back of the jaw near the joint, they pushed the older, smaller teeth forward. And because of the curved nature of the jaw cartilage, this forward progression forced the entire tooth row to curl downward and then inward upon itself, forming that characteristic spiral whorl within the floor of the mouth. The oldest, smallest teeth ended up tucked deep inside the spiral, essentially stored within the jawbone, while the newest, largest, sharpest teeth formed the functional, cutting edge along the outer curve. The upper jaw likely possessed flattened, crushing teeth, or perhaps simply closed down onto the lower spiral like a lid on a blender. Based on the size of the tooth whorls and comparisons with related species, Helicoprion was large. Some estimates suggest it reached lengths of 7.5 to 10 metres, roughly 25 to 33 feet, making it one of the top predators of the Permian seas. It belonged not to the true sharks, but to an extinct group of cartilaginous fish called the eugeneodontides, more closely related to modern ratfish and chimeras than to great whites or hammerheads. How did this internal buzzsaw function? The exact mechanics are still discussed, but the leading hypothesis is that Helicoprion specialised in hunting soft-bodied cephalopods, the abundant ammonites and squid of the Permian Ocean. As the animal closed its mouth on prey, the spiral in the lower jaw would rotate slightly, the teeth slicing backward and upward like a circular saw, cutting through the soft body of a squid or the tissue of an ammonite against the upper jaw or palate. The whirl acted as a combination saw and conveyor belt, processing food with remarkable efficiency. Helicoprion was clearly a successful creature. Its fossils span a wide geographic and temporal range, indicating it thrived for millions of years across the Permian seas and even survived into the early Triassic, outlasting the Great Dying, the worst mass extinction in Earth's history. That survival is a testament to the effectiveness of its unique feeding strategy. Eventually, however, even Helicoprion vanished from the fossil record, leaving behind only those enigmatic, beautiful and utterly perplexing spiral tooth whorls. To contemplate Helicoprion is to marvel at the sheer inventiveness of evolution when it comes to teeth, a puzzle that took over a century to solve. A giant shark-like fish with a rotating buzzsaw embedded in its lower jaw, silently cruising the ancient seas surrounding Pangaea. From the oceans, we move now to the freshwater world of the Permian, to the rivers, lakes, and swamps that dotted the interior of the great supercontinent. Because not all of the ocean's strangest creatures lived in the sea itself. Some haunted the inland waters, and none were stranger than the amphibian with a head shaped like a boomerang. This is Diplocaulus, the double stalk. Diplocaulus was a lepospondyle amphibian, a member of an extinct group of ancient four-legged animals that thrived during the Carboniferous and Permian periods. Its fossils have been found primarily in North America, especially in the red beds of Texas and Oklahoma, with some additional specimens known from the late Permian of Morocco. It was first described by the legendary American paleontologist Edward Drinker Cope in 1877, and it has been puzzling scientists ever since. Imagine a creature about 1 metre long, roughly 3 feet, with a stocky salamander-like body, short legs and a flattened tail adapted for swimming through the murky waters of ancient rivers and lakes. So far perhaps not too remarkable. A large ancient salamander-like animal, living at the bottom of Permian waterways, hunting fish and small invertebrates. Many such creatures existed during this period. But then you look at the head, and everything changes. The skull of Diplocaulus is unlike any other skull in the entire history of vertebrate life. 2 enormous bony projections, called tabular horns, extend laterally from the back of the skull, growing outward and backward like the arms of a boomerang. In adult specimens, these horns transform the head into a wide, flat, wing-shaped structure that is far wider than the body itself. In some individuals, the skull measures up to 15 centimetres across, which for a creature only 1 metre long is an extraordinary proportion. What possible purpose could such a bizarre head shape serve? The most widely accepted hypothesis, and the one supported by hydrodynamic experiments, is that the boomerang head functioned as a hydrofoil. Think of the wing of an airplane, or the blade of a propeller. When Diplocaulus tilted its head upward against the current of a river or stream, the broad flat shape of the skull would have generated significant lift, propelling the creature upward through the water with minimal muscular effort. Experiments using models of Diplocaulus schools in water tanks have confirmed that this shape does indeed produce substantial upward force when angled against a flow. This would have made Diplocaulus a remarkably effective ambush predator. Imagine it lying flat on the bottom of a shallow river, its mottled body blending with the mud and gravel. its eyes positioned on the top of its head, peering upward through the water. A small fish swims above unaware. Diplocaulus tilts its boomerang head upward. The current does the rest, lifting the creature off the bottom in a sudden powerful surge. Its wide jaws snap shut. The fish is caught. Other scientists have proposed alternative or complementary functions. Some suggest the horns made Diplocaulus difficult for predators like Dimetrodon to swallow, a kind of defensive width that would jam in the throat of any creature trying to gulp it down whole. Others have proposed that the horn supported a membrane of skin connecting the head to the body, making Diplocaulus look much larger and more intimidating than it actually was. And some have suggested the horns played a role in species recognition or mate selection. The truth may involve a combination of these functions. What is certain is that Diplocaulus was a successful creature, surviving for roughly 50 million years across the late Carboniferous and Permian periods, a remarkably long run for any animal. Juvenile specimens show that the tabular horn started small and grew progressively wider and more pronounced as the animal matured, achieving the full boomerang shape only in adulthood. This ontogenetic change, from small triangular skull to full boomerang, has been beautifully documented in growth series of fossils. Diplocaulus was an aquatic creature, spending most or all of its life in the water. There is evidence that during droughts, when its home rivers and ponds dried up, Diplocaulus would burrow into the mud to estivate, essentially hibernating until the rains returned and the water rose again. Fossil evidence of these burrows has been found in Texas, sometimes with multiple individuals huddled together underground, waiting out the dry season. In at least one case, the sail-backed predator Dimetrodon apparently dug into these burrows to feed on the trapped amphibians, a grim but vivid glimpse of life and death in the ancient Permian. To contemplate Diplocaulus is to wonder at the plasticity of the vertebrate skull, the incredible range of shapes that evolution can produce from the same basic set of bones. A boomerang-headed amphibian lying in wait at the bottom of a lost river, using the laws of hydrodynamics to ambush its prey. We move now to one of the most enduring mysteries in all of paleontology. A creature so strange, so stubbornly resistant to classification, that scientists have been arguing about what it even is for over 70 years. We travel to the Carboniferous period, roughly 307 million years ago, to the shallow brackish estuaries that once covered what is now the state of Illinois. And here, preserved in thousands of ironstone nodules in the remarkable Mazon Creek fossil beds, we find the Tully monster, Tullymonstrum gregarium, named after Francis Tully, the amateur fossil collector who first discovered it in the 1950s while splitting open rocks in the coal mining spoil heaps of northern Illinois. And a monster it truly seems, not in size, for it was relatively small, typically only 10 to 35 centimeters long. But in the sheer bewildering strangeness of its body plan, the Tully monster looks less like a single animal and more like a surrealist collage assembled from leftover parts of several entirely different creatures. Let us build its image carefully in our minds, based on the flattened, often faint, impressions left in those ironstone nodules. The body is soft, vaguely torpedo-shaped or slug-like, lacking any obvious fins, scales, or shell. It gives almost no immediate clues to its identity. Then extending from one end, presumably the front, is a long, stiff yet flexible proboscis, or snout, perhaps accounting for a significant portion of the creature's total length. And at the very tip of this strange extended snout is a small, claw-like structure lined with tiny sharp teeth. Imagine a grasping claw on the end of a rigid straw attached to a slug. And then there is the feature that makes the Tully monster truly unforgettable. Projecting outward from the sides of the main body, roughly midway along its length, is a rigid bar or stalk, like a cross-piece on a letter T, and perched at each end of this crossbar, far away from the head, far away from the proboscis, are two small dark oval structures, eyes. The eyes of the Tully monster sit at the ends of a rigid transverse bar sticking out sideways from the middle of its body, completely detached from the head region. Try to picture this creature swimming. How did it move? Perhaps by undulating its soft body, like a worm or a primitive fish. How did it see? Did that rigid eye bar provide some kind of panoramic, stereoscopic vision? How did it feed? Did it probe the muddy bottom with its long proboscis, snatching tiny invertebrates with its terminal claw? Or did it perhaps latch onto larger creatures feeding in some parasitic fashion? For decades, the Tully monster defied all classification. It was so utterly unlike anything else known, living or extinct, that scientists simply could not agree on where it belonged in the tree of life. Was it a bizarre mollusk, perhaps related to sea slugs or snails? Was it a strange type of segmented worm? Was it some kind of arthropod? Or was it something else entirely, representing a failed evolutionary experiment that left no relatives and no descendants? The mystery deepened with every new study. Despite thousands of specimens being found, all from this single fossil locality, none seemed to preserve the internal details needed to settle the debate. Then, in the mid-2010 era, several independent studies using advanced imaging techniques, including synchrotron scanning and chemical analysis of the fossils, proposed a truly surprising answer. They found evidence of what appeared to be a notochord, a primitive backbone-like structure. They identified possible gill pouches. They described muscle segments arranged in a V shape, features characteristic of vertebrates. The conclusion was startling. The Tully monster might actually be a vertebrate, a fish. Specifically a bizarre, soft-bodied relative of modern lampreys and hagfish, those jawless parasitic creatures that represent some of the most primitive living vertebrates, a fish pretending to be an invertebrate chimera. This vertebrate hypothesis seemed, for a time, to solve the riddle, but subsequent studies challenged the interpretation, pointing to inconsistencies in the evidence and reinterpreting the supposed vertebrate features. Some researchers argued that the Tully monster was more likely an invertebrate, after all, perhaps some kind of strange mollusk, or a member of a protostome lineage that has since gone entirely extinct. The scientific debate continues. The Tully monster remains stubbornly resistant to easy answers. It floats in our understanding, suspended between major branches of the animal kingdom, a creature whose very identity eludes our most sophisticated analytical techniques. Tullimonstrum gregarium is more than just a strange fossil. It is the official state fossil of Illinois, a designation that speaks to its cultural significance and its enduring hold on the public imagination. It is a symbol of scientific curiosity, a reminder that the deep past still holds genuine mysteries, puzzles that cannot be solved simply by throwing more technology at the problem. To contemplate the Tully monster is to embrace the unknown, to acknowledge the limits of our knowledge and to marvel at the sheer, almost playful strangeness that evolution is capable of producing. A soft-bodied riddle, drifting silently through the Carboniferous estuaries, its stalked eyes scanning a world we can only dimly imagine. If you are still with us, and I hope you are, perhaps drifting comfortably somewhere between waking and sleep, take this moment to breathe. We are roughly halfway through our journey tonight, and we have covered an immense span of time, from the Cambrian dawn over 500 million years ago to the coal swamps of the Carboniferous 300 million years ago. We have met creatures with 5 eyes, creatures with spiral saw teeth, creatures with boomerang heads, and creatures that scientists cannot even classify. If you have been enjoying this quiet exploration and would like to see more, a simple tap on the subscribe button helps these videos reach other people who might enjoy them too. And if you have not already, I would love to hear in the comments which creature has been your favourite so far, or which one you found the strangest. Sometimes the answers surprise me. Now let us continue. The ancient oceans are calling, and we have many more strange and wonderful creatures still to meet. We leave the Carboniferous and Permian behind now, and we cross one of the most terrible boundaries in the history of life on Earth. 252 million years ago, at the end of the Permian period, something catastrophic happened. Massive volcanic eruptions in what is now Siberia, eruptions so vast that they lasted for hundreds of thousands of years and covered an area the size of Western Europe in lava, pumped enormous quantities of carbon dioxide and other gases into the atmosphere. Temperatures soared, oceans acidified, oxygen levels in the water plummeted. The result was the Permian-Triassic extinction, often called the Great Dying, the most devastating mass extinction event in the entire history of life on this planet. Roughly 90 to 96% of all marine species were wiped out. The trilobites, which had survived for over 300 million years, vanished forever. The eurypterids, the great sea scorpions, were gone. Vast reefs collapsed. The oceans for a time were nearly empty. But life is resilient. Slowly, over millions of years, the survivors began to diversify to fill the empty niches left by the catastrophe. And among those survivors, a group of animals that had been relatively inconspicuous during the Permian began to make their move, the reptiles. Specifically, a diverse array of reptilian lineages that would, over the next 200 million years, produce some of the most extraordinary marine creatures the world has ever seen. We enter the Triassic period now, the age of recovery, roughly 250 to 200 million years ago. The supercontinent Pangaea still dominates the globe, though it is beginning to break apart. The Great Tethys Ocean, a warm tropical sea stretching between what would become Europe and Africa, is teeming once more with life, and haunting the shores and shallow coastal waters of this ancient ocean are creatures that push the boundaries of anatomy to extremes that seem almost impossible. The first of these is one of the strangest reptiles that ever lived, not because of its teeth, or its armour, or its eyes, but because of its neck. This is Tanystropheus, the long vertebra. Imagine a reptile perhaps 6 meters long from nose to tail, 20 feet. That is a respectable size, comparable to a large modern crocodile, but the proportions of Tanystropheus are unlike anything a crocodile, or any other living animal, can match. The body itself is relatively modest, perhaps somewhat lizard-like, with 4 sturdy limbs suggesting the creature could walk competently on land. The tail is long and tapering, useful perhaps for balance or for swimming, all fairly normal. But then there is the neck. The neck of Tanystropheus is simply extraordinary. It is incredibly long, slender and stiff, composed of only 13 cervical vertebrae. But each of those vertebrae is massively elongated, stretched out far beyond normal proportions. The result is a neck that accounts for roughly half of the creature's entire body length. 3 meters of pure neck, extending from a body that is perhaps only 2 meters long, not counting the tail. Imagine a reptile the size of a crocodile, but with the neck of a giraffe stretched out even further. When the first fossils of Tanystropheus were discovered, consisting often of just those incredibly long, hollow neck bones, paleontologists had no idea what they were looking at. Were these the limb bones of some unknown giant? The tail vertebrae of a bizarre swimming reptile? Some even suggested they might be the winged bones of a pterosaur, the flying reptiles that were just beginning to evolve during the Triassic. It took the discovery of more complete skeletons to reveal the astonishing truth. These were the neck bones of a single, profoundly weird reptile. How could such a structure possibly function? And what kind of lifestyle demanded such an extreme specialization? The neck vertebrae, though few in number, were enormously elongated and yet relatively lightweight, perhaps containing air sacs to reduce their mass. But they were also quite stiff, offering limited flexibility, except perhaps near the base where the neck joined the body, and close to the small head at the far end. This was not a supple, snake-like neck, capable of intricate bending and twisting. It was more like a long, jointed fishing rod, extending rigidly from the creature's shoulders. The prevailing scientific hypothesis, supported by a landmark study published in Current Biology in the 2020 by Stefan Speakman and colleagues is that Tanistropheus was a semi-aquatic ambush predator perfectly adapted to hunting in the shallow coastal waters of the Tethys Sea. Picture the scene. Tanistropheus stands or lies on the rocky shore, its relatively inconspicuous body hidden among stones or low vegetation. But that immense neck extends out over the water, reaching far into the shallows or even into deeper zones, projecting its small head into areas that would be completely inaccessible to a purely terrestrial predator. The long neck allowed Tanistropheus to reach prey without its larger body disturbing the water, without alerting fish or squid to its presence. Its small head, armed with sharp-pointed teeth in adult specimens, was perfect for snatching fish, squid, crustaceans or other small marine creatures that swam within range. Imagine the feeding strike. The body remains motionless, hidden. The long, stiff neck extends patiently through the water, the small head drifting almost imperceptibly. A fish swims too close, with a sudden swift movement of the head and the very tip of the neck, the only part perhaps capable of rapid motion. The jaws snap shut. The prey is caught. The neck retracts slowly, bringing the meal back to shore. It was a living fishing pole, a reptile that solved the problem of bridging the gap between land and sea, not by becoming fully aquatic, but by evolving one body part to an almost unbelievable extreme. Supporting evidence for this semi-aquatic lifestyle is strong. Tanistropheus fossils are typically found in marine deposits, alongside fish and other sea creatures. Some specimens show webbed feet, and interestingly, the tails of some Tanistropheus individuals have been found broken off, leading to speculation that, like some modern lizards, they may have been able to shed their tails as a defense mechanism if attacked by a larger marine predator while they were hunting with their necks extended in the water. Recent research has also revealed something fascinating about the growth of Tanistropheus. Juveniles appear to have had different teeth than adults, with juveniles possessing multicusped teeth suited for eating insects and small invertebrates, while adults had sharp, single-pointed teeth adapted for catching fish. This suggests that Tanistropheus may have changed its diet and possibly its habitat as it grew, with juveniles living more on land and adults spending more time hunting in coastal waters. Tanistropheus represents one of the most remarkable anatomical specializations in the history of vertebrate life. To contemplate this creature is to be confronted with the sheer plasticity of the reptilian form, the incredible lengths, quite literally, to which evolution will go to exploit an ecological opportunity. A reptilian fishing rod, patiently waiting by the shores of a lost ocean. Sharing the coastal waters of the Tethys Sea with the impossibly long-necked Tanistropheus was another marine reptile, one that represents a more conventional but still fascinating step in the reptilian conquest of the ocean. This is Nothosaurus, the false lizard. Nothosaurus lived during the Triassic period, from roughly 240 to 210 million years ago, and its fossils have been found across what is now Europe, North Africa and China. It was a sauropterygian, a member of the great group of marine reptiles that would eventually give rise to the famous plesiosaurs and pliosaurs of the Jurassic and Cretaceous periods. In many ways, Nothosaurus represents the early experimental stage of that lineage, a creature that had not yet fully committed to life in the open ocean. Imagine a sleek, elongated reptile, perhaps 3 to 4 meters long, with a long neck, a relatively narrow skull lined with sharp needle-like teeth that interlocked when the jaws closed, and a long tapering tail. Its limbs are webbed but not yet fully transformed into flippers. They still retain distinct fingers and toes, suggesting that Nothosaurus was capable of hauling itself out of the water and moving, perhaps awkwardly, on land. Think of it as the marine reptile equivalent of a modern seal, a creature comfortable in both water and on shore, but increasingly specialized for an aquatic lifestyle. In the water, Nothosaurus was a fast and agile hunter. Its webbed feet and long tail provided propulsion and maneuverability, and those interlocking needle teeth were perfectly designed for one thing: catching fish. Imagine it darting through a school of small Triassic fish, its narrow head slicing through the water, its jaws snapping shut on a silvery prize, those teeth meshing together like the bars of a cage, preventing any escape. Nothosaurus likely spent much of its time in the coastal shallows, hunting in waters near the shore and returning to land to rest, to bask in the Triassic sun, and perhaps to breed. Its lifestyle was probably not unlike that of modern seals or sea lions, animals that are supremely adapted to the water but have not entirely severed their connection to the land. The significance of Nothosaurus lies in what it represents in the broader story of marine reptile evolution. It is a transitional form, a snapshot of the moment when reptiles were still experimenting with the aquatic lifestyle that their descendants would perfect. The plesiosaurs that came later, with their fully paddle-like flippers and their complete adaptation to open ocean life, evolved from ancestors very much like Nothosaurus. It is the bridge between the shore and the deep sea, the intermediate step on a journey that would produce some of the most formidable marine predators the world has ever known. To picture Nothosaurus is to imagine the busy sun-drenched shorelines of the Triassic Tethys Sea, reptiles basking on warm rocks, slipping into the shallows to hunt, their sleek bodies cutting through the water with increasing grace and efficiency. A preview of the reptilian marine revolution that was about to transform the oceans of the Mesozoic. We jump forward now, past the end of the Triassic and through the Jurassic period, into a time when marine reptiles have fully conquered the open ocean. The plesiosaurs are cruising the deep with their long necks and their powerful paddle-like limbs. The ichthyosaurs, those reptilian dolphins, are racing through the water at speeds no marine animal has achieved before. And lurking among them, patrolling the warm, shallow seas that covered large parts of Eurasia, is a creature that looks less like a marine reptile and more like something from a monster movie. This is Dacosaurus, and its appearance is so unusual among marine reptiles that when paleontologists first studied it in detail, they gave it an unofficial nickname that captures its strangeness perfectly. They called it Godzilla. Dacosaurus was a crocodilomorph, a member of the same broad group that includes modern crocodiles and alligators, but it was not a crocodile in any sense that we would recognize today. It lived during the late Jurassic and early Cretaceous periods, from roughly 157 to 137 million years ago, and it was fully adapted to a life at sea. Imagine a creature about 5 meters long, roughly 16 feet, with an elongated body that bears a superficial resemblance to a modern crocodile. It has the same general layout of 4 limbs and a long tail, but the limbs of Dacosaurus are not the sturdy, sprawling legs of a river-dwelling crocodile. They have been modified into paddle-like flippers, perfectly suited for steering and manoeuvring in open water. The tail is likely flattened or fin-like, providing powerful propulsion. This was a creature built for swimming, not for basking on riverbanks. But the truly strange thing about Dacosaurus, the feature that earned it the Godzilla nickname, is its head. Most marine crocodilomorphs of the Mesozoic had long, narrow snouts, similar to a modern gharial, perfectly shaped for snapping up fish in the water. Dacosaurus was different. Its skull was short, deep, and massive, more like the head of a large carnivorous dinosaur than a typical marine crocodile. The teeth were large, serrated, and blade-like, designed not for delicate fish catching, but for tearing into large muscular prey. This combination of a fully marine body with a dinosaur-like skull made Dacosaurus a unique and formidable predator. It likely hunted other marine reptiles, large fish, and anything else it could overpower in the warm Jurassic and early Cretaceous seas. It was not a pursuit predator in the way that an ichthyosaur was. Its body was probably not built for sustained high-speed chases, but as an ambush predator, lurking in the mid-water or rising suddenly from below, its short, powerful jaws would have been devastating. Fossil evidence suggests that Dacosaurus may have spent its entire life at sea. never returning to land. This is unusual for a crocodilomorph. Modern crocodiles, even saltwater species, still come ashore to nest, but Dacosaurus may have mated, and perhaps even given live birth in the open water, a lifestyle more comparable to a dolphin or a whale than to anything we associate with crocodiles today. Described in detail by researchers including Zulma, Gasparini, and colleagues, with particularly well-preserved specimens found in Argentina and Germany, Dacosaurus represents yet another remarkable evolutionary experiment. A crocodile that abandoned the rivers and the shorelines, grew flippers instead of feet, evolved a short, crushing skull unlike any of its marine relatives, and became a top predator of the open Mesozoic seas. To contemplate Dacosaurus is to appreciate the incredible diversity of form that crocodilomorphs achieved during the age of dinosaurs. These were not just river-dwelling ambush predators. They were a sprawling, diverse group that experimented with everything from terrestrial galloping to open ocean swimming to, in the case of Dacosaurus, a hunting style that looked more like a marine dinosaur than a crocodile, a genuine sea monster with a dinosaur's head and a dolphin's body, cruising through the warm, shallow seas of the ancient world. Let us pause here for a moment and simply breathe. We have been travelling through time at an extraordinary pace, leaping across millions of years between each creature, each era, each strange and wonderful inhabitant of the ancient seas. But the ocean does not move at that pace. The ocean moves slowly, the currents turn in great, patient circles. The tides advance and retreat with the steady rhythm of the moon. The sediment drifts down through the water column like the slowest possible snow, settling grain by grain on the floor of the abyss, building the geological record one atom at a time. So let us slow down for a moment. Let the ancient waters hold us, and let us visit three more creatures that deserve their place in this story. Creatures we passed over in our rush through the ages, but whose strangeness and beauty are too remarkable to leave in the dark. We return first to the Triassic period, roughly 220 million years ago, and to the coastlines of what is now the western United States. The Triassic, as we have seen, was a time of recovery and experimentation, when life was filling the empty ecological niches left by the Great Dying. On land, the first dinosaurs were beginning their ascent. In the air, the first pterosaurs were learning to fly. And in the ocean, a group of marine reptiles was evolving that would, in time, become some of the most successful ocean predators the world has ever known. These were the ichthyosaurs, the fish lizards. Ichthyosaurs are one of the great success stories of marine evolution. They first appeared in the early Triassic, evolved rapidly into a staggering diversity of forms, and persisted all the way through to the mid-Cretaceous period, a span of over 150 million years. At their peak, they were found in every ocean on Earth, from the tropical shallows to the polar seas. They evolved a body plan that converged remarkably on that of modern dolphins and tuna, a streamlined torpedo-shaped body, a vertical tail fin for powerful thrust, a dorsal fin for stability, and large, forward-facing eyes for keen vision in the water. But among the ichthyosaurs, one genus stands out for its sheer, almost unbelievable size. This is Shonisaurus, the lizard from the Shoshone Mountains, and it was a giant among giants. Shonisaurus lived during the late Triassic, roughly 227 to 208 million years ago. Its fossils have been found in what is now Nevada, in deposits that represent an ancient shallow sea that once covered the western part of North America. The most famous fossil site is Berlin Ichthyosaur State Park, near the town of Gabs, Nevada, where dozens of Shonisaurus skeletons have been found preserved together on a single ancient seafloor. The reasons for this mass death remain debated, but the site provides an unparalleled window into the biology and possible social behaviour of these extraordinary creatures. The size of Shonisaurus is staggering. The largest species, Shonisaurus sicaniensis, described from British Columbia, Canada, may have reached lengths of 21 metres, roughly 69 feet. That is larger than a modern sperm whale, larger than a school bus, larger than any other marine reptile known from the Triassic. It was one of the largest animals on the planet at the time of its existence, rivaled in size only by the very largest of the giant orthocone nautiloids that had ruled the oceans hundreds of millions of years before. Imagine this creature, swimming through the warm, shallow Triassic seas. Its body is immense, barrel-shaped and streamlined, adapted for cruising at moderate speeds through the open water. Its eyes are large, perhaps the better to spot prey in the dimmer light of deeper water. Its snout is long and relatively narrow, and here is where Shonisaurus becomes particularly interesting. Adult Shonisaurus appear to have been largely or entirely toothless. Juvenile specimens possess teeth, but as the animals matured their teeth were lost, resulting in a smooth, edentulous jaw. This is unusual for a large marine predator, and has led to considerable debate about how adult Shonisaurus fed. Without teeth, it could not have bitten or chewed its prey. The most widely accepted hypothesis is that large Shonisaurus were suction feeders, using the rapid opening of their long jaws to create a powerful inward rush of water that would draw soft-bodied prey, squid, fish, and other cephalopods directly into their mouths. This feeding strategy is used today by some species of beaked whales and by the modern sperm whale, which also has a relatively elongated, somewhat toothless upper jaw and feeds primarily by suction. Picture a school of Shonisaurus, perhaps a dozen of these immense, sleek creatures, moving together through the Triassic Ocean. Their bodies undulate with slow, powerful strokes of their crescent-shaped tail fins. Their huge eyes scan the water ahead. They are searching for schools of squid, the abundant cephalopods that thrive in these warm seas. When they find their prey, the hunt is not a dramatic chase. It is a patient, deliberate process. Each Shonisaurus opens its long jaws with a sudden rapid expansion, and the suction pulls the squid in, one by one, like a living vacuum cleaner sweeping through the water. The mass death site in Nevada adds another layer of intrigue. Why were dozens of these enormous animals found together in one place? Some scientists have suggested it was a mass stranding event, similar to modern whale beachings. Others have proposed that it might be a calving ground, a place where pregnant females gathered to give birth. Like modern ichthyosaurs, Shonisaurus almost certainly gave live birth in the water, tail first, like modern dolphins. A nursery site would explain the concentration of individuals in a relatively small area. Shonisaurus represents the ichthyosaurs at their most grandiose, their most whale-like, their most impressive. It is a reminder that long before the whales evolved, long before the dolphins and the porpoises, the oceans were already home to air-breathing, live-birthing, fish-shaped reptiles of enormous size. The ichthyosaurs invented the dolphin body plan over 200 million years before dolphins did, a stunning example of convergent evolution driven by the relentless physical demands of life in the open ocean. A giant toothless predator the size of a whale cruising through the Triassic seas with a school of its own kind. Another astonishing product of the ocean's endless capacity for reinvention. We leap forward now to the early Cretaceous, roughly 120 to 100 million years ago, and we sink below the surface of the warm, shallow seas that cover much of what is now Australia. Here, patrolling the waters with the brutal efficiency of a submarine built for war, is one of the most fearsome marine reptiles of the entire Mesozoic era. This is Kronosaurus, named after Kronos, the king of the Titans in Greek mythology, the god who devoured his own children. The name is appropriate. Kronosaurus was a pliosaur, a member of the short-necked branch of the plesiosaur family, while the long-necked plesiosaurs, the ones that inspired the popular image of the Loch Ness Monster, were graceful long-necked swimmers that probably fed on fish. The pliosaurs were something very different. They were the heavy artillery of the Mesozoic seas, short-necked, massive-headed, immensely powerful, built not for grace, but for raw, overwhelming predatory force. and Kronosaurus was among the largest and most powerful of them all. The size of Kronosaurus has been the subject of some debate. Early estimates, based on a famous mounted skeleton at Harvard University's Museum of Comparative Zoology, suggested a total length of over 12 meters, roughly 40 feet. However, it was later discovered that this mount included too many vertebrae, artificially inflating the animal's length. More recent estimates place Kronosaurus at roughly 9 to 10.5 meters, roughly 30 to 34 feet in total length. That is still enormous, comparable in length to a large modern orca, but in Kronosaurus the proportions tell the real story. The skull alone measured over 2.5 meters, roughly 8 feet in length. That means the head accounted for nearly a quarter of the entire body. Imagine an animal the size of an orca, but with a head that takes up a quarter of its body length. A head that is almost nothing but jaw, and what jaws they were. Kronosaurus possessed massive conical teeth, some of them exceeding 7 centimeters in length, set in jaws that could exert tremendous biting force. These were not the slicing teeth of a mosasaur or the piercing fangs of a pliosaur like Leopleurodon. These were crushing teeth, designed for gripping and demolishing heavily armoured prey. The skull was built for power, with enormous jaw muscles anchored to a broad, robust cranium. What did Kronosaurus eat? The evidence points to a diet of large, tough prey. Sea turtles, with their thick protective shells, were likely a staple. Ammonites, with their coiled calcareous shells, would have posed no challenge to those crushing jaws. Large fish and other marine reptiles were undoubtedly consumed. One particularly dramatic piece of evidence comes from a fossil Kronosaurus specimen that was found with the remains of a smaller plesiosaur in its stomach region. The king of the Titans lived up to its name. Kronosaurus swam using its 4 large, powerful flippers, a style of locomotion unique to plesiosaurs and pliosaurs. Unlike ichthyosaurs, which used their tails for propulsion, or mosasaurs, which undulated their bodies, plesiosaurs essentially flew through the water, using their flippers like underwater wings, rowing and flapping through the ocean with a motion that combined elements of bird flight and turtle swimming. Computer modelling and biomechanical studies have shown that this mode of propulsion was surprisingly efficient, and the pliosaurs with their shorter necks and more hydrodynamic body shapes were likely among the fastest of the plesiosaur lineage. Imagine Kronosaurus now, cruising through the warm Cretaceous seas off ancient Australia. Its massive head, the largest proportional head of almost any marine predator in history, is held slightly forward, its eyes scanning for prey. Its 4 flippers beat with steady, powerful strokes. It spots a large sea turtle drifting in the mid-water. With a sudden burst of speed, it closes the distance. Those enormous jaws open, the teeth clamp down. The sound of shell cracking echoes through the water. The king of the Titans has fed. Kronosaurus went extinct along with all other pliosaurs during the Cretaceous, victims of the same environmental changes that would eventually claim the mosasaurs and the dinosaurs. But for millions of years it was among the most formidable marine predators on the planet, a creature built entirely around the concept of a massive, crushing bite. Before we rejoin our main narrative on its path through the Cenozoic and the age of mammals, there is one more ancient ocean creature that demands our attention. Not because it was large. In fact, it was relatively small by the standards of the predators we have been discussing, and not because it was the most successful or the most widespread or the most ecologically important, but because it is, without question, one of the strangest looking sharks that has ever existed. This is Stephacanthus, the chest spine, but it is more commonly known by a far more evocative nickname, the ironing board shark. Stephacanthus lived during the late Devonian and Carboniferous periods, roughly 380 to 320 million years ago, in the shallow seas and coastal waters of what is now North America, Europe, and Asia. It was a small shark, perhaps 70 centimeters to 2 meters in length depending on the species. In most respects it looked like a relatively conventional early shark, with a streamlined body, a heterocircle tail fin, and the general proportions you might expect from a primitive shark of the Paleozoic era. But then there was the thing on its back. Rising from the dorsal surface of the male Stephacanthus, in the position where most sharks have a normal, blade-like dorsal fin, was a structure that looked like nothing else in the entire history of fishes. Instead of a conventional fin, there was a broad, flat, anvil-shaped or T-shaped platform, like a tiny ironing board or a mushroom cap, perched on top of a short stalk. And the flat upper surface of this bizarre structure was covered in a dense brush of tiny tooth-like denticles, sharp backward-pointing scales that gave the platform a rough, sandpaper-like texture. To make things even stranger, the top of the shark's head, the area directly in front of this dorsal platform, was also covered in a similar patch of enlarged denticles, creating a matching rough surface on the skull. What possible purpose could this extraordinary apparatus serve? The honest answer is that we do not know for certain, but several hypotheses have been proposed, and the most widely discussed involves visual deception. When viewed from above, or from directly ahead, the combination of the flat, denticle-covered platform on the back and the matching denticle patch on the head may have created an illusion. The rough, tooth-like texture of both surfaces, viewed together, might have resembled a giant open mouth, full of teeth, belonging to a much larger creature. In other words, the ironing board may have been a form of mimicry, making the small Stephacanthus appear to a predator looking down from above, like the gaping mouth of a far more dangerous animal. This is speculative, of course. Other scientists have suggested the structure played a role in mating, acting as a display organ to attract females or intimidate rival males. The fact that the bizarre dorsal platform appears to be present only in males supports this interpretation. Perhaps it functioned like the elaborate plumage of a peacock, serving no practical purpose beyond sexual advertisement. Or perhaps it served as a suction disc of some kind, allowing the shark to attach itself temporarily to larger marine animals, though this hypothesis is less widely supported. Whatever its function, the ironing board dorsal fin of Stephacanthus is one of the most visually striking and inexplicable features in the entire fossil record of sharks. It is a reminder that the shark lineage, which we often think of as relatively conservative in form, has produced its own share of wildly experimental designs over the course of its 400 million year history. Not every shark looked like a great white. Some looked like nothing you could possibly imagine. Picture a small, sleek shark swimming through the dim warm waters of a carboniferous shallow sea. On its back, where a normal dorsal fin should be, rises that strange flat denticle-covered platform, like a tiny billboard advertising something we can no longer understand. It is a creature designed by evolution in one of its more whimsical moods, a shark with a built-in ironing board, another small but unforgettable resident of the ocean's cabinet of curiosities. We return now to the open ocean and to a creature that is often overlooked in discussions of marine giants, perhaps because it lacks the dramatic jaws of a Dunkleosteus or the terrifying reputation of a megalodon. It was not a predator. It was not armoured. It had no bizarre appendages or bewildering body plan. And yet, in terms of sheer size, it may have been one of the largest fish that has ever swum through any ocean on Earth. This is Leedsichthys, the Leeds fish, named after Alfred Nicholson Leeds, the English farmer and fossil collector who first discovered its bones in the clay pits of Peterborough, England, in the 1880s. Leedsichthys lived during the Middle to Late Jurassic period, roughly 165 to 155 million years ago, in the warm, shallow seas that covered much of Europe. It was a pachycormid, a member of an extinct family of bony fish that were among the largest ray-finned fish ever to evolve, and Leedsichthys was the largest of them all. Estimating the size of Leedsichthys is notoriously difficult. Its fossils tend to be fragmentary, and the bones are often scattered and incomplete, perhaps because the sheer size of the animal meant that its carcass took a long time to sink and was thoroughly scavenged and dispersed before burial. Early estimates suggested lengths of up to 27 metres, making it potentially the largest fish of all time. More recent, more conservative analyses, based on careful scaling from the better preserved skeletal elements, have revised this downward to perhaps 16 to 17 metres, roughly 52 to 56 feet for the largest individuals. That is still enormous, comparable in length to a modern whale shark, which holds the title of the largest living fish. But here is what makes Leedsichthys truly interesting. Despite its colossal size, it was a gentle giant, a filter feeder. Like the modern whale shark and the modern basking shark, Leedsichthys possessed a specialised gill apparatus that allowed it to strain enormous quantities of plankton, small fish and other tiny organisms from the water as it swam slowly through the Jurassic seas with its mouth agape. Imagine this creature now. A fish the size of a bus, perhaps larger, moving with slow, ponderous grace through the warm, plankton-rich waters of the Jurassic Ocean. Its mouth is wide, its gill arches lined with fine comb-like rakers that sieve the water, trapping the clouds of tiny organisms that drift in the currents. It is not hunting, it is harvesting. Sweeping through the ocean like a living trawler, processing cubic meters of water with every stroke of its enormous tail. This is a feeding strategy that has evolved independently several times in the history of ocean life. In the Jurassic, Leedsichthys filled this niche. In the modern ocean, the whale shark and the basking shark have convergently evolved remarkably similar lifestyles, despite being completely unrelated to Leedsichthys. And of course, the great baleen whales, which are mammals, not fish, have taken the concept of filter feeding to its most extreme expression, with the blue whale, the largest animal ever to live, straining tons of krill from the sea every day. The fact that this same strategy has evolved again and again in completely different lineages across hundreds of millions of years tells us something profound about the ocean. There is always a living to be made from the small, the invisible, the countless, the plankton, the krill, the larvae, the tiny drifting organisms that fill every cubic metre of seawater. These represent an inexhaustible resource for any creature large enough and specialised enough to harvest them efficiently. And the ocean has always rewarded those who learn to eat from the bottom of the food chain, rewarding them with the gift of enormous size. Leedsichthys shared its Jurassic seas with some of the most fearsome predators of the Mesozoic, including large marine crocodilomorphs and the great pliosaurs. It was undoubtedly preyed upon. Tooth marks from marine predators have been found on some Leedsichthys bones, and it is easy to imagine a pliosaur or a large shark targeting a juvenile or a weakened individual. But the adults, at over 15 metres in length, would have been formidable targets, and their sheer size was likely their primary defence. Leedsichthys went extinct in the late Jurassic, perhaps around 155 million years ago. The reasons are unclear, but changes in ocean circulation and plankton productivity during the transition from the Jurassic to the Cretaceous may have reduced the food supply that these enormous filter feeders depended upon. To contemplate Leedsichthys is to imagine the ocean at its most productive and its most peaceful. A colossal fish, swimming slowly, mouth agape, filtering the Jurassic sunlight through a curtain of water and plankton. A gentle giant in an ocean ruled by teeth. Let us drift now, through a longer passage of time, and let the creatures we have met settle into the quiet spaces of your memory. The ocean is still around us, still holding us, still vast and dark and full of history. We have travelled so far tonight. From the first strange experiments of the Cambrian, 540 million years ago, through the armoured nightmares of the Devonian, through the spiral-jawed mysteries of the Permian, through the reptilian empires of the Mesozoic, and into the age of whales and sharks that followed. Every era had its monsters, every age had its experiments, every ocean in every epoch produced creatures that would seem impossible if we did not have the fossils to prove they were real. And yet, for all the strangeness we have encountered, there is a pattern, a rhythm, a set of themes that recurs again and again across the immense canvas of ocean history. The theme of convergence, the observation that the same body shapes, the same feeding strategies, the same solutions to the problems of swimming and hunting and surviving evolve over and over again in completely unrelated lineages. The dolphin shape, independently invented by ichthyosaurs, by dolphins, and by certain fast-swimming fish. The filter-feeding strategy, independently developed by Leetsichthys, by basking sharks, by whale sharks, by baleen whales, and by the flamingo-like pterosaur Pterodaustro, which we glimpsed in our outline but did not visit tonight. The crushing jaw, evolved separately by Dunkleosteus, by Kronosaurus, by Deinosuchus, and by the modern alligator. The ocean, it seems, has a limited set of best answers to its physical challenges, and life keeps discovering them independently, again and again, across hundreds of millions of years. The theme of arms races, the endless escalation between predator and prey, each driving the other to new extremes of size, speed, armour, and weaponry. The trilobites evolved hard shells, perhaps in response to the grasping arms of Anomalocaris. The placoderms evolved heavier armour, but Dunkleosteus evolved jaws that could cut through it. The ammonites evolved thicker coils, but Helicoprion evolved a rotary saw to slice them open. The whales grew larger, but Leviathan evolved teeth the size of bowling pins to bring them down. Every innovation by prey drives a counter-innovation by predator, and the result is the staggering diversity and the escalating strangeness of ocean life through time. And the theme of loss, the quiet, persistent drumbeat of extinction that accompanies every page of the fossil record. Every creature we have met tonight is gone. Every one. The trilobites, the placoderms, the ichthyosaurs, the mosasaurs, the ammonites, megalodon, basilosaurus, Leviathan, all of them erased by the slow turning of the Earth's climate, by the sudden violence of asteroid impacts, by the subtle shifting of ocean currents and atmospheric chemistry. The ocean is a generous mother, endlessly creative, endlessly productive, but she is also unforgiving. When conditions change, even the most successful, most powerful, most perfectly adapted creatures can be swept away, and the ocean moves on, filling the empty spaces with new experiments, new forms, new strangeness. This is the lesson of deep time, that nothing is permanent, that even dominance, even perfection, is temporary, that the ocean will always outlast its children. And so we arrive at the end of our journey, but perhaps the ending is not truly an ending. The ocean is still here. It covers 70% of the surface of this planet. It is still producing strange and wonderful creatures, still experimenting, still trying out new combinations of form and function that we have not yet discovered. The deep ocean, the lightless zones below 1,000 meters, remains one of the least explored environments on Earth. New species are described every year, some of them as strange and as baffling as anything in the fossil record. The ocean has not stopped being creative. It has not run out of ideas. Perhaps somewhere in the blackness of the abyss there are creatures alive right now that would astound us as much as Opabinia or Anomalocaris astounded the paleontologists who first reconstructed them. Creatures with body plans we have never imagined, feeding strategies we have never conceived, solutions to the challenges of survival that are as elegant and as bizarre as anything the Cambrian produced. We may never find them. The deep ocean guards its secrets jealously, but they are there, drifting silently in the dark, waiting to be discovered. And that thought, that the strangeness of the ocean is not confined to the past, that the creative engine of evolution is still running, still producing marvels, gives a certain hopefulness to the end of our story. The creatures we have met tonight are gone. Yes, their fossils are all that remain, but the ocean that produced them is still here, still vast, still deep, still mysterious, and it is still, even now, at this very moment, producing the strange and wonderful creatures of tomorrow. Let that be the final thought that carries you into sleep. The ocean is ancient and patient. It has been producing miracles for 4 billion years, and it shows no signs of stopping. Somewhere beneath the waves, right now, something strange and beautiful is being born. We have travelled more than 500 million years tonight. We have sunk to the muddy floors of Cambrian seas and soared above the wave, topped on wings wider than a car. We have watched armoured fish crush bone with sharpened plates and gentle giants filter plankton through gaping mouths. We have felt the terrible suction of Dunkleosteus, the patient stillness of Deinosuchus, the impossible geometry of Diplocolus, and the spiralling mystery of Helicoprion. These were real creatures. They are gone now, all of them, dissolved back into the stone from which we briefly summoned them. But their strangeness endures, their stories endure, and the ocean that made them endures, covering most of this planet in a layer of water that is older than any mountain, deeper than any canyon, and more full of history than any library ever built. The water remembers, even if the fossils are silent. Thank you for joining me tonight, for sinking down into these ancient seas and letting the strange parade of deep-time ocean life drift past you. I hope you found something to wonder at. I hope you found something that surprised you, or puzzled you, or made you see the ocean just a little differently. And now, let the water close gently above you. Let the last of the light fade. Let the strange and wonderful creatures of deep time drift away into the darkness, back into the stone, back into the silence of the deep. They will be there whenever you want to visit again. Rest well. The ocean will keep its secrets safe until morning. Good night. We move forward now, deeper into the Cretaceous period, the final act of the age of dinosaurs. The oceans of the late Cretaceous, from roughly 82 to 66 million years ago, are among the most well-studied and most terrifying marine environments in the history of the planet. The ichthyosaurs have declined and vanished. The plesiosaurs still cruise the deep, their long necks trailing through the currents. But the undisputed rulers of these seas, the apex predators that dominated every ocean on Earth during the final chapter of the Mesozoic, are the mosasaurs. And the largest, the most famous, and arguably the most formidable of them all is Mosasaurus, the moose lizard, named after the river in the Netherlands near which its first fossils were discovered in the 1760s. Mosasaurus was not a dinosaur. It was a marine reptile, a member of the order Squamata, the same group that includes modern lizards and snakes. In fact, mosasaurs are most closely related to monitor lizards, the family that includes the Komodo dragon. Imagine a Komodo dragon, but stretched out to enormous proportions, with its limbs evolved into powerful paddles, its tail flattened into a swimming fin, and its entire body adapted for a life spent entirely in the ocean. That gives you a rough idea of what Mosasaurus was, though the reality was far more impressive and far more terrifying than any simple comparison can capture. The size of Mosasaurus varied by species, but the largest, Mosasaurus hoffmanni, may have reached lengths of 13 to 17 metres, roughly 43 to 56 feet. That puts it in the range of a modern humpback whale, though considerably more slender and far more predatory. Its body was streamlined and muscular, built for efficient cruising through the water. Its 4 limbs had evolved into broad, flat paddles, used not for propulsion but for steering and stability. The main source of thrust was the tail, which was long, muscular, and equipped with a vertically oriented tail fin, providing the powerful undulating strokes that drove this enormous animal through the Cretaceous seas. The skull of Mosasaurus was long, robust, and filled with teeth, and the teeth are worth describing, because they tell us a great deal about how this creature lived and fed. Mosasaurus possessed not 1, but 2 rows of teeth in its upper jaw. The outer row lining the main jawbone consisted of large, conical, slightly recurved teeth, designed for seizing and holding prey, but there was also an inner row of teeth on the pterygoid bones, the bones that form part of the roof of the mouth. These inner teeth acted like a conveyor belt, helping to walk prey backward into the throat once it had been seized by the outer teeth. This double-rowed dental arrangement is similar to what we see in modern snakes, and like snakes, mosasaurs possessed a remarkable degree of jaw flexibility. The lower jaw was not rigidly fused at the front as it is in most mammals. Instead, the two halves of the lower jaw were connected by a flexible ligament, allowing them to spread apart slightly, enabling Mosasaurus to swallow prey larger than might otherwise seem possible. The skull itself was somewhat kinetic, with some degree of movement between the bones, further enhancing the gape and the feeding efficiency of this magnificent predator. What did Mosasaurus eat? The answer is virtually everything. Fossil evidence, including stomach contents preserved in some specimens, reveals a staggeringly varied diet. Fish, of course, were a staple. Ammonites, those coiled-shelled cephalopods that were so abundant in the Cretaceous seas, have been found in Mosasaurus gut contents, their shells cracked and fragmented by those powerful jaws. Sea turtles, including individuals with shells that should have offered some protection, were clearly no obstacle. Sharks fell prey to mosasaurs. Plesiosaurs, those other great marine reptiles, were consumed. Even other mosasaurs were on the menu. Mosasaurus was the ultimate opportunist, an apex predator that feared nothing and ate everything. The first Mosasaurus fossils were discovered in a chalk quarry near the city of Maastricht in the Netherlands, sometime around 1764. The skull that was found, enormous and lined with those distinctive conical teeth, created a sensation in the scientific world and became one of the most famous fossils of the 18th century. It played a role in the early development of paleontology as a science, helping to establish the idea that species could go extinct, a concept that was still controversial at the time. Mosasaurs as a group were globally distributed, their fossils found on every continent including Antarctica. They dominated the world's oceans for roughly 20 million years during the late Cretaceous, diversifying into dozens of species adapted to different prey and different habitats. Some were small and slender, suited for catching fish in shallow waters. Others, like the mighty Mosasaurus hoffmanni, were the undisputed apex predators of the open ocean. They vanished, along with the dinosaurs, the pterosaurs and the ammonites, in the mass extinction event at the end of the Cretaceous, 66 million years ago, when an asteroid impact and its cascading environmental consequences brought the Mesozoic era to a catastrophic close. To contemplate Mosasaurus is to imagine the ocean at its most dangerous, a time when a creature the size of a whale, with the jaws of a giant lizard and the appetite of a shark, ruled every sea on Earth, a quiet, efficient, endlessly adaptable predator perfectly suited to its world. The lizard that became a leviathan, closely related to Mosasaurus, and sharing the same Cretaceous seas, was another mosasaur that deserves its own moment in our journey. While Mosasaurus is perhaps the most famous, Tylosaurus may have been the most fearsome. Tylosaurus, the knob lizard, lived during the late Cretaceous, from roughly 89 to 66 million years ago, and its fossils are particularly well known from the chalk deposits of Kansas, a region that during the Cretaceous was covered by the Western Interior Seaway, the vast shallow ocean that split North America in two. In many ways, Tylosaurus resembled its cousin Mosasaurus. It was large, powerful, streamlined, and thoroughly adapted to marine life, but Tylosaurus had its own distinctive features that set it apart. The most notable of these was its elongated, solid, bony snout, a blunt, rounded rostrum extending forward beyond the first row of teeth. This structure has no analogue in any modern marine predator. Some scientists believe it was used as a ramming weapon, allowing Tylosaurus to deliver devastating headbutts to stun or injure prey before closing in with its teeth. Others suggest it may have been used for intraspecific combat, with males ramming each other during disputes over territory or mates. Tylosaurus was one of the largest of all mosasaurs. The biggest individuals may have exceeded 13 meters, over 43 feet in length, Its body was powerful and muscular, its tail thin, broad and strong. Its jaws were equipped with the same general arrangement of large conical teeth and palatal teeth found in other mosasaurs, designed for seizing, holding and swallowing large prey, whole or in chunks. And the diet of Tylosaurus, revealed through the extraordinary fossil record of the Western Interior Seaway, was spectacularly varied. Stomach contents and associated remains found with Tylosaurus specimens include fish, sharks, smaller mosasaurs, plesiosaurs, seabirds, and even a flightless diving bird called Hesperornis, a creature that itself was adapted for an aquatic lifestyle. Tylosaurus appears to have been an indiscriminate predator, eating whatever it could catch and overpower. In the rich, productive waters of the Western Interior Seaway, there was plenty to eat. The Western Interior Seaway itself is worth pausing to imagine. It was a shallow, warm sea that at its maximum extent stretched from the Gulf of Mexico all the way to the Arctic Ocean, cutting North America cleanly in half. On the western side lay the mountainous landmass of Laramidia, home to Tyrannosaurus and Triceratops. On the eastern side lay Appalachia, a lower, flatter landmass, and between them this vast inland sea, perhaps only a few 100 meters deep at most, was one of the most productive marine ecosystems in the history of the planet. It teemed with fish, ammonites, sea turtles, sharks, and marine reptiles of every description, and at the top of the food web, surveying this abundance with cold, efficient eyes, swam Tylosaurus. The fossil record of the Western Interior Seaway is extraordinarily rich, and much of what we know about mosasaurs, including Tylosaurus, comes from decades of collecting in the chalk deposits of Kansas, particularly the Smoky Hill chalk member of the Niobrara Formation. Pioneers of mosasaur research, including the legendary fossil collector Charles H. Sternberg and paleontologist Michael Everhart, have devoted their careers to documenting the remarkable fauna of this ancient sea. To contemplate Tylosaurus is to imagine the warm, shallow waters of an ocean that no longer exists, teeming with life, dominated by a predator that combined the body of a sea serpent with the skull of a battering ram and the appetite of a shark. Another magnificent and terrifying product of the age of reptiles. We remain in the late Cretaceous for one more creature, but we leave the open ocean and move to the shoreline, to the river mouths, the estuaries, the shallow coastal waters where the boundary between land and sea blurs, and the dangers of both worlds converge. Because the giant mosasaurs were not the only enormous predators prowling the Cretaceous waterways. There was something else, something that waited at the water's edge, something that hunted the very dinosaurs that walked the land. This was Deinosuchus, the terrible crocodile. Picture a modern saltwater crocodile, the largest living reptile today, a creature that can reach 6 or even 7 meters in length and weigh over a metric ton. Now scale that up by a lot. Deinosuchus was not just a large crocodile, it was a colossal one. Based on fossil skulls, some measuring nearly 2 meters, 6 feet in length, and extrapolations from the proportions of related species, paleontologists estimate that the largest Deinosuchus individuals reach lengths of 10 to 12 meters, roughly 33 to 40 feet. This makes it one of the largest crocodilians ever known, significantly larger than any species alive today, and approaching the body length of Tyrannosaurus rex itself. The skull of Deinosuchus was a fortress. Incredibly robust, broad and heavily built, it was designed for one thing above all else, delivering crushing, devastating bites. The jaws were equipped with numerous large, thick conical teeth, some the size of bananas, designed not for the delicate fish catching of a gharial or the slicing of a mosasaur, but for crushing bone and shattering shells. Biomechanical analyses suggest that Deinosuchus possessed a bite force that was truly extraordinary, potentially rivaling or even exceeding that of Tyrannosaurus rex. The sheer pressure those jaws could exert was sufficient to crack the thick shells of the largest sea turtles and to crush the bones of large dinosaurs. And that is exactly what Deinosuchus, appears to have done. Fossil evidence paints a vivid and chilling picture of this creature's lifestyle. Bite marks found on the bones of hadrosaurs, the large duck-billed dinosaurs that were among the most common herbivores of the late Cretaceous, have been matched with the size and spacing of Deinosuchus teeth. These marks appear on leg bones, tail vertebrae, and other parts of the skeleton, strongly suggesting that Deinosuchus regularly ambushed dinosaurs at the water's edge. Imagine a herd of hadrosaurs, perhaps Parasaurolophus or Coryphosaurus, approaching a river to drink. The day is hot, the water is inviting. They step cautiously into the shallows, lowering their broad flat heads to the surface. But beneath that surface, invisible, motionless, utterly patient, lies Deinosuchus, a creature capable of remaining perfectly still for hours, its body temperature regulated by the warm water around it, its eyes and nostrils barely breaking the surface, blending with the murky river like a log or a mudbank. Then the strike, explosive, violent, irresistible. The enormous crocodile lunges with terrifying speed, its immense jaws clamping down on the leg or snout of the unsuspecting hadrosaur. The dinosaur bellows, struggles, tries to wrench free, but the weight and power of Deinosuchus are overwhelming, combined perhaps with the infamous crocodilian death roll, that spinning, twisting maneuver that modern crocodiles use to tear off pieces of prey too large to swallow whole. The dinosaur is dragged into the water. In the murky depths, the struggle ends. Deinosuchus was not a specialist. It was an opportunist. Sea turtles, with their thick protective shells, were clearly on the menu, and the crushing power of those jaws was perfectly suited for cracking them open. Large fish were undoubtedly consumed, but it was the ability to prey on dinosaurs, to bridge the gap between the aquatic and terrestrial worlds in the most terrifyingly predatory way imaginable, that made Deinosuchus truly unique. This creature lived during the late Cretaceous, roughly 82 to 73 million years ago. Recent research by Adam Cossett and Christopher Brochu, published in 2020, revised the taxonomy of Deinosuchus, recognizing multiple species and clarifying their geographic ranges. Fossils have been found across the southern and eastern United States, from Montana to New Jersey, suggesting that Deinosuchus inhabited a wide range of coastal and estuarine environments. As conditions changed toward the end of the Cretaceous, perhaps as the western interior seaway retreated and the warm, shallow environments that Deinosuchus preferred diminished, this magnificent crocodilian declined and eventually vanished. It was replaced by smaller, more adaptable crocodilian lineages, some of which survive to this day. To contemplate Deinosuchus is to imagine the most dangerous waterhole in the history of the planet, a place where the simple act of taking a drink could be your last. It is to picture a predator of almost mythical proportions, a true terrible crocodile that embodied the raw, brutal power of the reptilian reign at its absolute peak. An armoured behemoth, patient and silent, the undisputed bone-crushing king of the Cretaceous shoreline. And then, 66 million years ago, the world changed forever. An asteroid, roughly 10 to 12 kilometers across, struck the Earth near what is now the Yucatan Peninsula in Mexico, creating the Chicxulub impact crater and unleashing a cascade of destruction that no large animal on the planet could escape. The impact itself generated shockwaves that circled the globe. Tsunamis hundreds of meters high swept across the oceans. Wildfires ignited across entire continents, and in the months and years that followed, as dust and debris from the impact filled the atmosphere, blocking sunlight and plunging the Earth into a prolonged catastrophic winter, the food chains that had sustained the Mesozoic world collapsed. The dinosaurs, except for the lineage that had already evolved into birds, were gone. The pterosaurs, those magnificent flying reptiles that had ruled the skies for over 150 million years, were gone. The mosasaurs, the great marine lizards that had dominated every ocean on Earth, were gone. The plesiosaurs, the ammonites, the belemnites, countless other groups that had thrived for tens of millions of years, all vanished in what seemed like the blink of a geological eye. The oceans, so recently teeming with reptilian giants, were suddenly and profoundly empty. But not for long. We enter now the Cenozoic era, the age of mammals. In the aftermath of the extinction, the survivors, many of them small, many of them seemingly insignificant during the age of dinosaurs, began their great diversification. On land, mammals of bewildering variety evolved to fill the vacant ecological niches. Horses, elephants, cats, dogs, primates, all the familiar lineages trace their explosive diversification to the aftermath of the asteroid. And in the oceans, a similar revolution was underway. A group of land-dwelling mammals, perhaps small hoofed creatures resembling a cross between a tiny deer and a dog, began to spend more and more time in the water. Over millions of years their bodies transformed. Their legs shortened and flattened into flippers, their tails broadened into flukes, their nostrils migrated to the tops of their heads. They became whales. But the early whales, the first ones to complete the transition from land to sea, were not the gentle giants we associate with the word today. They were something far stranger, something far more predatory. And the most famous, most bizarre, and in some ways most terrifying of these early whales has a name that, like the creature itself, is deeply misleading. This is Basilosaurus, the king lizard. The name is wrong. Basilosaurus is not a lizard, not a reptile, not a dinosaur. It is a mammal, a whale, one of the earliest fully aquatic whales in the fossil record. The misleading name was given in 1834 by the American naturalist Richard Harlan, who first described fossils from Alabama that he thought belonged to some kind of enormous marine reptile. Harlan examined the long vertebral bones, compared them to the bones of large dinosaurs, and concluded that his creature was even larger than Megalosaurus or Iguanodon. He named it Basilosaurus, king of the lizards. It was not until the famous British anatomist Richard Owen examined the specimen more carefully, studying the teeth in particular, that the truth emerged. The molar teeth were double-rooted, a feature found in mammals, but never in reptiles. The creature was not a lizard at all, it was a whale. Owen proposed renaming it Zeuglodon, meaning yoked tooth, but by the rules of zoological naming, the original name, however inaccurate, had priority, and so the creature that is perhaps the strangest whale that ever lived carries the name of a lizard king forever. Basilosaurus lived during the late Eocene epoch, roughly 41 to 34 million years ago. Its fossils have been found primarily in the two regions. The type species, Basilosaurus cetoides, is known from the southeastern United States, particularly Alabama, Mississippi, and Louisiana, where its fossils are so common that it was designated as the official state fossil of Alabama. The second major species, Basilosaurus isis, has been found in extraordinary abundance in Egypt, particularly in the Fayum Depression and at Wadi el Hitan, the Valley of the Whales, a UNESCO World Heritage Site where over 500 ancient whale skeletons have been excavated. The size of Basilosaurus was impressive. Basilosaurus cetoides measured 17 to 20 meters long, roughly 56 to 66 feet. Basilosaurus isis was slightly smaller, perhaps 15 to 18 meters. A recent study from 2025 estimated that a large Basilosaurus cetoides might have weighed 15 metric tons. These were among the largest animals on the planet during the Eocene, and they were undoubtedly the apex predators of their oceanic world. But the body of Basilosaurus looked nothing like a modern whale. Forget the rounded, blubber-padded shape of a humpback or a blue whale. Basilosaurus was long, slender, almost serpentine, more like a giant eel or a sea snake than a whale as we understand the term. Its body was enormously elongated, with vertebrae in the midsection that were uniquely stretched to 3 times the length of comparable bones in other whales. giving it a sinuous, undulating form that must have been both graceful and slightly unnerving to behold. Its skull was relatively small for its body size, and it housed a brain that was also small, far smaller in proportion to its body than the brains of modern whales. This suggests that Basilosaurus lacked the intelligence and the complex social behaviours that characterise many living cetaceans. It probably could not echolocate. It almost certainly did not form the tight-knit social pods that modern dolphins and whales are known for. It was likely a solitary creature, a lone hunter cruising the warm Eocene seas. But what Basilosaurus lacked in brain power, it made up for in bite force. Its skull was robust, with powerful jaw muscles, and its teeth were extraordinary. The front teeth were conical and pointed, designed for seizing and gripping prey. But the cheek teeth, the premolars and molars further back in the jaw, were something special. They were large, triangular, and bore multiple sharp cusps or serrations, creating a shearing surface that could slice through flesh and bone with devastating efficiency. These teeth were capable of genuine occlusion, meaning the upper and lower teeth fit together and worked against each other, allowing Basilosaurus to chew its food, something that modern toothed whales, which swallow their prey whole, cannot do. Studies of Basilosaurus bite force, based on analysis of scarred skull bones of other whale species found alongside Basilosaurus fossils, have estimated that it could exert a maximum bite force of at least 16,400 newtons, and possibly over 20,000 newtons. That is comparable to the bite force of modern alligators and crocodiles. For a marine mammal, it was extraordinary, and the evidence of what Basilosaurus did with that powerful bite is written in the fossil record. Stomach contents preserved in Basilosaurus cetoid specimens have revealed the remains of large fish and sharks, but perhaps most dramatically, the skulls of Dorudon, a smaller species of ancient whale that shared the same Eocene seas, have been found bearing bite marks that precisely match the dentition of Basilosaurus isis. Basilosaurus appears to have regularly hunted and killed other whales. In 2015, a complete Basilosaurus skeleton was uncovered at Wadi el Haitan in Egypt, preserved with the remains of its last meal still inside, including a Dorudon and several species of fish. It is one of the most complete records of predation in the entire fossil record, a snapshot of violence preserved for 40 million years. There is one more extraordinary detail about Basilosaurus that cannot go unmentioned. Basilosaurus still had legs, tiny vestigial hind limbs, complete with a functional knee joint and even toes, protruded from the rear of its elongated body. These legs were far too small to be used for walking or swimming. They were useless for the locomotion of any kind. But they were clearly still functional in some capacity, and the most widely accepted hypothesis is that they were used as clasping guides during mating, helping these enormous serpentine creatures align their bodies during the act of reproduction. These tiny legs are a profound piece of evidence. They are the remnants of the land-dwelling past that Basilosaurus had so recently left behind. Just a few million years before Basilosaurus swam the seas, its ancestors were walking on those legs, on dry land, living as terrestrial mammals. The legs of Basilosaurus are a physical record of one of the most dramatic transitions in the history of life, the return of mammals to the sea. Basilosaurus vanished at the end of the Eocene, roughly 34 million years ago, likely driven to extinction by the abrupt global cooling that marked the transition to the Oligocene epoch. It did not give rise to modern whales. It was a specialized, ultimately dead-end lineage, a magnificent experiment that succeeded brilliantly for several million years and then disappeared as the world changed around it. To contemplate Basilosaurus is to imagine the warm, shallow seas of the Eocene teeming with the very first whales, and among them a serpentine giant, solitary and powerful, hunting other whales with jaws that could crush bone, while tiny useless legs trailed behind its body like ghosts of a landlocked past. The king lizard that was really a whale, another strange and unforgettable creature from the deep history of the ocean. We move forward now from the warm Eocene seas of Basilosaurus to the somewhat cooler but still remarkably productive oceans of the Miocene epoch, roughly 10 million years ago. Life in the sea has continued to diversify. Modern whales, both the toothed whales and the great baleen whales, have evolved and spread across every ocean. Dolphins and porpoises dart through the waves. Seals and sea lions haul out on rocky shores. Sharks of every shape and size patrol the depths. The marine world is beginning to look more familiar, more recognizable to our modern eyes. But familiar does not mean safe, because swimming through the Miocene seas of what is now Peru, South America, was a predator that makes even the modern sperm whale look gentle by comparison. A whale that did not feed on squid in the darkness of the deep ocean, as modern sperm whales do, but that hunted other whales in the sunlit waters near the surface, using the largest functional teeth of any animal that has ever lived. This is Leviathan melvilli, the Leviathan of Melville. The story of this creature's discovery reads almost like fiction. In November of 2008, on the very last day of a field expedition to the Pisco Formation in the coastal desert of Peru, a researcher named Klaus Post, working with the Natural History Museum Rotterdam in the Netherlands, stumbled across something extraordinary. Jutting from the ancient marine sediments roughly 35 kilometers southwest of the city of Ica was the partially preserved skull of an enormous whale. Not just any whale. A skull 3 meters long, 10 feet, massive and robust, lined with teeth of staggering proportions. The fossils were prepared in Lima and are now housed in the collection of the Museum of Natural History at the National University of San Marcos. When the describing team, led by Olivier Lambert of the Royal Belgian Institute of Natural Sciences, published their findings in the journal Nature in 2010, they initially named the creature Leviathan after the biblical sea monster. Herman Melville, the author of Moby Dick, had frequently referred to whales as leviathans in his novel, and naming this ancient predator after both the myth and the novelist seemed perfect. However, there was a problem. The name Leviathan had already been used, back in 1841, for a mastodon, even though that mastodon was later reclassified under the name mammoth. Under the rules of zoological nomenclature, a name, once used, cannot be reused for a different animal, and so the team was forced to find an alternative. They chose Leviathan, the original Hebrew spelling of the word Leviathan, and the species name Melville, honouring Herman Melville and his great white whale. Leviathan was a physeteroid, a sperm whale, but it was utterly unlike the modern sperm whale that bears the same family name. The modern sperm whale, Physeter macrocephalus, is a deep-diving specialist that feeds primarily on giant squid, using echolocation to find its prey in the pitch blackness of the deep ocean. It has teeth only on its lower jaw, and those teeth are relatively small and peg-like, not really designed for biting or chewing but for grasping slippery squid. Leviathan was nothing like this. Leviathan had massive functional teeth in both its upper and lower jaws, and these teeth were not small pegs. They were enormous, up to 36 centimeters long, 14 inches, roughly the length of a bowling pin. They are the largest functional teeth of any animal known to science. Elephant tusks are longer, of course, but tusks are not used for eating. The teeth of Leviathan were used for one purpose, killing and consuming large prey. Based on the size of the skull and comparisons with other sperm whales, Leviathan is estimated to have measured 13.5 to 17.5 meters in length, roughly 44 to 57 feet. Its weight may have reached 40 to 57 metric tons. It possessed a robust skull with powerful jaw muscles and almost certainly had a spermaceti organ, the large fluid-filled sac in the head of sperm whales that is used for echolocation. This means Leviathan could probably sense its prey from great distances, using sophisticated biosonar to track other whales moving through the Miocene waters. What did Leviathan eat? The answer is other whales. Specifically, medium-sized baleen whales, which were abundant and diverse during the Miocene. Leviathan was a hypercarnivore, a term meaning that more than 70% of its diet consisted of meat. It likely hunted near the surface, not in the deep ocean, using its size, speed, and devastating bite to overpower and kill whales that were themselves quite large. Imagine the encounter. A pod of medium-sized baleen whales, perhaps early relatives of modern humpbacks or grey whales, moving through the productive coastal waters of Miocene Peru. Beneath them, rising from the mid-depths, comes Leviathan. Its huge, squared-off head, housing that powerful echolocation organ, is pointed directly at its target. It accelerates, perhaps using its massive body to ram the victim, stunning it. Then the jaws open, revealing those colossal teeth. The bite is catastrophic. 36-centimeter teeth, driven into flesh and bone, with a force that scientists have called the largest tetrapod bite ever found. Leviathan shared its Miocene world with another legendary predator, the giant shark Megalodon. These two apex predators likely competed directly for the same prey, medium-sized whales in the same waters. Whether they ever confronted each other directly, whether a Leviathan ever fought a Megalodon, is unknown and perhaps unknowable. But the thought of these two colossal predators coexisting in the same ocean, each supremely adapted for killing, is one of the most awe-inspiring images in all of paleontology. Isolated teeth similar to those of Leviathan have been found far from Peru. In Chile, Argentina, South Africa, Australia, and even California, suggesting that either Leviathan itself or a close relative had a global or near-global distribution during the late Miocene and possibly survived into the Pliocene until roughly 5 million years ago. Its extinction was likely driven by the cooling of the oceans at the end of the Miocene, which reduced the populations of the medium-sized baleen whales upon which it depended. As its prey diminished, this magnificent predator could no longer sustain itself. To contemplate Leviathan is to imagine the most powerful bite in the history of whale evolution. Teeth the size of bowling pins, a skull 10 feet long, a predator that hunted other whales in the sunlit waters of a lost ocean. Named after a biblical sea monster and a literary masterpiece, Leviathan melvillei was the real Moby Dick, and it was far more terrifying than anything Herman Melville could have imagined. And now we arrive at the creature that needs, perhaps, the least introduction of any animal in our entire journey tonight. The most famous prehistoric ocean predator, the one that has inspired movies, documentaries, conspiracy theories, and more internet debate than any other extinct marine species, the giant shark, whose very name has become synonymous with prehistoric ocean terror. This is Megalodon, Otodus megalodon, the great tooth. Before we discuss its size, its teeth, and its reign of terror across the Miocene and Pliocene oceans, let us first address something important. Megalodon is extinct. Despite persistent rumours, despite breathless videos on social media claiming to show shadowy shapes in the deep ocean, despite the popularity of movies that imagine it lurking in the Mariana Trench, there is absolutely no credible scientific evidence that Megalodon still exists. It went extinct roughly 3.5 million years ago, during a period of global ocean cooling in the Pliocene epoch. The waters it needed, warm, productive, and rich in large prey, disappeared as the Earth slipped toward the ice ages. Megalodon died with them. That said, what Megalodon was, when it was alive, is more than enough to inspire awe without any need for fictional resurrection. Megalodon was a shark. It belonged to the family Ottodontidae, an extinct lineage of mega-toothed sharks that are related to but distinct from the modern great white shark. For many years, Megalodon was classified in the same genus as the great white, Carcharodon, leading to the popular conception of Megalodon as simply a giant version of a great white. More recent research, however, has placed it in its own genus, Otodus, reflecting its distinct evolutionary lineage. The exact size of Megalodon is debated, because like all sharks, its skeleton was made of cartilage, not bone. Cartilage does not fossilize well, and no complete Megalodon skeleton has ever been found. What we do have in enormous abundance are teeth. Megalodon teeth are large, triangular, beautifully serrated along both edges, and absolutely unmistakable. Individual teeth can measure up to 18 centimeters, roughly 7 inches, in slant height. They are found on every continent, on every coastline where Cenozoic marine rocks are exposed, a testament to the global distribution and long reign of this extraordinary predator. Based on the size and proportions of these teeth, and on comparisons with the tooth-to-body ratios of living sharks, paleontologists have estimated the size of Megalodon. The numbers vary depending on the methodology used, but most estimates place the maximum length at 15 to 18 meters, roughly 49 to 60 feet. Some researchers have proposed even larger sizes, up to 20 meters or more, though these upper estimates are more speculative. At the conservative end, a 15-meter Megalodon would have been roughly 3 times the length of the largest great white shark ever recorded. At the upper end, it would have been comparable in length to a humpback whale. The weight of such a creature is difficult to estimate precisely, but figures in the range of 30 to 50 metric tons are commonly cited. This was a massive animal, far heavier than any modern shark. The teeth tell us a great deal about how Megalodon lived. They are broad, flat, and serrated, very different from the narrow pointed teeth of a fish eater. These are teeth designed for one thing, biting large chunks out of very large prey. The serrations act like steak knives, allowing the tooth to saw through flesh, blubber, and even bone with each bite. When Megalodon bit down, it did not seize and hold, the way a great white often does. It removed material. Imagine a cookie cutter the size of a dinner plate, driven by the most powerful jaws in the history of shark evolution, and the bite force was truly staggering. A landmark study led by Stephen Rowe and colleagues, published in 2008, used computer modelling to estimate the bite force of Megalodon, and concluded that it was the most powerful bite of any creature that has ever been reliably measured or estimated. The maximum bite force was calculated at between 108,000 and 182,000 newtons. For comparison, the estimated maximum bite force of Tyrannosaurus rex is roughly 35,000 to 57,000 newtons. A modern great white shark generates about 18,000 newtons. Megalodon's bite was in a category all its own, capable of crushing the thick bones and shells of anything in the Miocene ocean. What did Megalodon eat? The fossil record provides clear answers. Its primary prey were whales. Fossil whale bones have been found bearing distinctive bite marks that match Megalodon teeth, with enormous chunks removed from ribs, vertebrae, and flippers. These marks are found on a wide variety of whale species, from small dolphins to medium-sized baleen whales. Seals and sea lions were also likely on the menu, as were large fish, sea turtles, and essentially anything else that Megalodon could catch. There is evidence that Megalodon's hunting strategy changed as it grew. Isotopic analysis of Megalodon teeth and vertebrae, published by researchers including Kenshu Shimada, suggests that juvenile Megalodons inhabited warm, shallow coastal nursery areas where they fed on smaller prey. As they grew larger and more powerful, they ventured into deeper, colder waters to pursue the bigger quarry, the whales and other large marine mammals that only an adult Megalodon could tackle. This ontogenetic shift in habitat and diet is similar to what we see in some modern sharks and suggests a degree of behavioural complexity. Megalodon reigned for roughly 20 million years, from the early Miocene to the mid-Pliocene. During this time it was the undisputed apex predator of the global ocean. Nothing challenged it, nothing competed with it successfully, though Leviathan, which we met earlier, came closest. It shaped the ecology of the Miocene seas, driving the evolution of its prey species, influencing the distribution and behaviour of whales and other marine mammals across the planet. Its extinction, roughly 3.5 million years ago, coincided with a period of significant global cooling. As the Earth entered the series of glacial cycles that would eventually produce the Pleistocene ice ages, ocean temperatures dropped, particularly in the temperate and high latitude regions. The warm, productive waters where Megalodon hunted and bred contracted toward the tropics. The great baleen whales, its primary prey, began to migrate to colder, more productive waters that were physiologically unsuitable for Megalodon. Cut off from its food source, unable to breed successfully in its shrinking habitat, the greatest shark that ever lived slowly, inexorably declined. The last Megalodon died in an ocean that was growing colder, emptier, and less hospitable with every passing century. To contemplate Megalodon is to imagine the sea at its most powerful and its most dangerous, a creature that could bite through whale bone with the force of a hydraulic press, a predator so successful that it dominated every ocean on Earth for 20 million years. And yet even Megalodon, for all its power, could not survive the slow, relentless turning of the climate. A humbling reminder that no creature, however large, however fearsome, is immune to the forces that reshape our planet. We leave the sharks now and the whales, and we turn our eyes upward for our final creature of the evening, not beneath the waves, but just above them, skimming the surface of ancient oceans, riding the wind on wings wider than any bird alive today. This is Pelagornis sandersi, the bony-toothed glider. Pelagornis belongs to a family of birds called the Pelagornithids, often nicknamed the pseudo-toothed birds, and they are among the most remarkable flying animals that have ever existed. They first appeared in the fossil record shortly after the extinction of the dinosaurs in the Paleocene epoch, and they persisted for an astonishing span of time, surviving all the way through to the Pliocene, just a few million years ago. For over 50 million years, these enormous seabirds soared above the world's oceans, and their fossils have been found on every continent, including Antarctica. The most complete and most impressive specimen of this group is Pelagornis sandersi, described by paleontologist Daniel Kozepka in 2014, based on a remarkably well-preserved skeleton discovered during airport construction in Charleston, South Carolina. The bones were found in Oligocene age deposits, roughly 25 to 28 million years old, and they told an astonishing story. Pelagornis sandersi had an estimated wingspan of 6 to 7.5 meters. That is 20 to 24 feet across. To put that in perspective, the modern wandering albatross, the largest flying bird alive today, has a wingspan of roughly 3.5 meters. Pelagornis was nearly double that. Its wingspan approached that of a small aircraft, a Cessna or a Piper. And yet this was a living, breathing bird, constructed of bone, feather and muscle. How could a bird that size possibly fly? The answer lies in its construction. The bones of Pelagornis were incredibly thin-walled and hollow, pneumatized to an extreme degree, making them extraordinarily light relative to their size. The bird's body, despite its immense wingspan, was probably not much heavier than a large modern albatross. It was built for one thing and one thing only: soaring. Like the albatross, Pelagornis was almost certainly a dynamic soarer, exploiting the differences in wind speed at different altitudes above the ocean surface to travel enormous distances with minimal flapping. It could ride the ocean winds for days, perhaps weeks, crossing entire oceans without ever needing to rest on land. Taking off would have been the challenge. A bird this large could not simply leap into the air from a standing start. It almost certainly needed a running start, perhaps launching itself from a cliff edge or from the crest of a wave, spreading those immense wings and catching the wind in a single, committed leap of faith. But once airborne, it was a creature of supreme efficiency, a silent, immense shadow drifting above the waves. And then there is the beak, the feature that gives the pseudo-toothed birds their name. Birds lost their true teeth early in their evolutionary history, soon after they diverged from their dinosaurian ancestors. No modern bird has teeth, but Pelagornis and its relatives found a remarkable workaround. Lining the edges of its long, slender beak, both upper and lower, were rows of sharp, pointed projections made of bone. These were not true teeth. They were extensions of the jawbone itself, covered in the same keratinous material as the rest of the beak. But they functioned like teeth, forming a jagged saw-like edge along the entire length of the bill. These pseudo-teeth were clearly an adaptation for catching and holding slippery marine prey. Imagine Pelagornis swooping low over the ocean surface, its enormous wings barely clearing the wave tops. It spots a fish or a squid swimming just beneath the surface. It dips its long beak into the water, scooping upward. The jagged pseudo-teeth grip the prey like the tines of a fork, preventing it from wriggling free of that slippery, wet beak. The catch is secure. The bird tilts its head back and swallows. This is convergent evolution at its finest. Birds lost their teeth, but evolution found a way to give them back, reinventing a tooth grip from a completely different raw material. It is an elegant, almost playful solution to a practical problem, and it speaks to the endless creativity of the evolutionary process. The Pelagornithids were clearly a successful group. Their 50-million-year reign across the global oceans is a testament to the effectiveness of their design. They outlasted multiple climate changes, multiple shifts in ocean currents and productivity, but eventually in the Pliocene, they vanished. The reasons are not entirely clear. Perhaps changes in ocean wind patterns disrupted the atmospheric conditions they depended on for soaring. Perhaps changes in the distribution or abundance of surface-dwelling fish and squid reduced their food supply. Perhaps competition from newly evolving marine mammals, seals and sea lions, or from other seabird lineages played a role. Whatever the cause, the pseudo-toothed birds are gone, and nothing like them exists in the modern world. The wandering albatross is the closest living analogue, a large soaring seabird that rides the ocean winds for thousands of miles. But even the albatross, magnificent as it is less than half the size of Pelagornis. To contemplate Pelagornis is to imagine the vast empty horizons of ancient oceans, and above them, silently, a bird with the wingspan of a small aircraft, gliding on invisible currents of wind. Its jagged beak cuts through the spray. Its shadow drifts across the waves like the passage of a cloud. It is another reminder of the scale and the strangeness that life can achieve, another ghost from a world that is gone. Our journey through the strangest extinct sea animals is drawing to its close now. We have travelled more than 500 million years, from the soft experimental mud of the Cambrian seafloor to the wind-swept surface of the Miocene ocean. We have met creatures with 5 eyes, creatures with spiral saw jaws, creatures with boomerang heads and impossibly long necks. We have encountered sharks that could crush whalebone, whales that hunted other whales, crocodiles that ambushed dinosaurs, and birds with wingspans wider than a car is long. Every one of these creatures was real. Every one of them lived, breathed, hunted, and died in the oceans of this planet. The same planet where you are lying now, perhaps drifting closer to sleep. The sound of this voice a quiet companion in the darkness. But as we contemplate these recovered ghosts, these fragments pieced together from silent stone, we must also acknowledge a profound and humbling truth. The creatures we have met tonight, the ones whose names we know, whose forms we can reconstruct, represent only an infinitesimally small fraction of the life that has ever existed in the oceans of Earth. Fossilization is not the rule. It is the vanishingly rare exception. For a creature to become a fossil, it must die in exactly the right place, at exactly the right time. It must be buried quickly by sediment, before its body can be scattered by currents or consumed by scavengers. Its hard parts, bones, teeth, shells, must be slowly replaced by minerals over millions of years, preserving their shape in stone. And then that stone must survive, unbroken, uncrushed, uneroded, for tens or hundreds of millions of years, until finally a human being happens to crack open the right rock in the right place and sees a shape that should not be there. The odds against any individual organism becoming a fossil are astronomical. The odds against an entire species leaving behind recognizable fossils are only slightly better. And for soft-bodied creatures, animals made entirely of flesh and cartilage and jelly, with no hard parts to preserve, the odds are essentially zero. The only reason we know about creatures like Opabinia and Hallucigenia is because of extraordinary geological accidents. Places like the Burgess Shale, where conditions were somehow perfect for preserving the impressions of soft bodies in fine-grained mud. Think about what this means. For every Opabinia we have found, how many equally strange, equally wonderful soft-bodied creatures lived and died in the Cambrian seas and left no trace at all? For every Basilosaurus, how many other bizarre early whales swam through the Eocene oceans and vanished without a fossil to their name? For every megalodon tooth we pick up on a beach, how many other extraordinary sharks lived and went extinct and left nothing behind but the memory of their absence? The fossil record is not a complete encyclopedia of past life. It is a tattered, fragmentary manuscript with perhaps one legible word on every 1,000 pages. The vast majority of the story of ocean life is simply missing, lost forever to the erosive forces of time, to the relentless recycling of the Earth's crust through plate tectonics, to the quiet dissolution of bone and shell in acidic water, to the simple, unforgiving truth that most things that die are never preserved. Imagine the creatures we will never know, forms perhaps even stranger than anything we have encountered tonight, life in the deep ocean, in the lightless zones far below the reach of sunlight, where fossilization is almost impossible, and entire ecosystems may have risen and fallen without leaving a single trace. Life in the open water column, where the bodies of pelagic creatures drift and dissolve, and are consumed long before they can settle to the preserving sediment of the seafloor. Life in environments so ancient, so deeply buried, so completely recycled by the geological processes of a 4.5 billion-year-old planet, that their very existence is beyond our ability to detect. The strangeness we have found, the 5 eyes, the buzzsaw jaws, the boomerang heads, the serpentine whales, all of it serves as a tantalizing hint of the true, unfathomable depth of the ocean's forgotten diversity. It suggests that the reality of the past was likely far richer, far weirder, and far more complex than even our most imaginative reconstructions can capture. And perhaps that is the most fitting thought to carry with you as you drift towards sleep. That the ocean, even the ocean of today, is built on an unimaginable foundation of lost life. That beneath every wave there is a history stretching back billions of years, populated by creatures we will never see, whose shapes we will never know, whose stories were never written in stone. The greatest strangeness of all may lie not in the fossils we hold, but in the echoes of the lives that left no echo at all, the silent, invisible majority of evolution's lost children, drifting forever in the deep, dark waters of time. Let that thought carry you now. The ancient ocean is still here, all around us, holding its secrets, and somewhere in the darkness, in the silence between the waves, the strange and wonderful creatures of deep time are still swimming, still waiting, still dreaming in the stone. Good night. Consider for a moment what the Cambrian Ocean actually sounded like. We tend to imagine the prehistoric world in silence, as if the creatures we reconstruct from stone existed in a void, moving through their ancient environments without sound or vibration. But the ocean has never been silent. Even 500 million years ago, the water itself was full of noise. The grinding of sediment along the seafloor, the click and rasp of small arthropod limbs against rock, the rush of currents through narrow channels between reefs of ancient sponges, the pulse of water through the bodies of swimming creatures, a low rhythmic thrum that would have been audible if there had been ears sophisticated enough to hear it throughout the water column. This was the soundscape of the Cambrian, not the whale song and dolphin click of the modern ocean, but something older, something more mechanical, something built from the movements of hard shells and soft bodies and the endless, restless stirring of the sea itself. Into this world Upperbinia drifted. Through this world an Amalakaris hunted. On the floor of this world Hallucigenia walked, its spines bristling, its soft legs probing the ancient mud. We carry this soundscape with us as we move forward through time, because the ocean never falls truly silent. It changes. It deepens. The creatures that inhabit it grow larger, grow louder, grow more complex. But the water itself remains, and the water remembers. As we travelled through the Devonian, the age of fishes, we witnessed the evolution of jaws and the arms race that followed. But we did not pause long enough to appreciate what the Devonian ocean looked like, not just in terms of its inhabitants, but in terms of its sheer physical beauty. The Devonian was the age of the first great coral reefs, tabulate corals and rugose corals, neither of which survives today, built enormous structures on the shallow continental shelves, creating underwater landscapes of staggering complexity. Sponges, some of them reaching several meters in height, form towering columns and delicate lattices. Crinoids, the sea lilies, covered every available surface, their feathery arms waving in the currents like underwater flowers. Brachiopods, hundreds of species of them, carpeted the seafloor in dense jostling communities. It was into this richly textured, architecturally complex world that Dunkleosteus swam. When we picture this armoured giant cruising through the Devonian seas, we should not imagine it moving through empty, featureless water. We should imagine it navigating a landscape as complex and as beautiful as a modern coral reef, threading its massive armoured body between towering sponge columns and fields of swaying crinoids, its self-sharpening jaw plates glinting in the dim, filtered light that penetrated the warm, shallow water. And we should imagine what happened when Dunkleosteus died, because even the death of a predator is part of the ocean's story. When a large Dunkleosteus sank to the sea floor, its massive heavy head shield settling into the mud, its body would have become a feast. Smaller fish, scavenging arthropods, ancient worms and snails would have converged on the carcass, stripping the flesh, consuming the soft tissues, leaving behind only those incredible armoured plates and jaw blades. Over time, sediment would cover the remains, minerals would slowly infiltrate the bone, molecule by molecule replacing the original material with stone, and 380 million years later, a human being would split open a rock in Ohio or Morocco and find, staring up at them, the face of a monster from a world that no longer exists. This is how the fossil record is built, one death at a time, one fortunate burial at a time, one slow molecular replacement at a time. It is a process of unimaginable patience, operating on timescales that dwarf anything in human experience, and yet it is the only window we have into the deep past. Every creature we have met tonight came to us through this process. Every set of five-eyed storks, every spiral tooth whirl, every boomerang skull was preserved by the same quiet, patient alchemy of death and stone and time. When we spoke of the Permian and Carboniferous waters and the strange creatures that inhabited them, we touched only briefly on the world that surrounded them. But that world deserves a moment of our attention, because the Carboniferous swamps and estuaries were among the most productive ecosystems in the history of the planet. The atmosphere during the Carboniferous contained roughly 35% oxygen, compared to roughly 21% today. This supercharged air allowed arthropods, those creatures that breathe through a network of tiny tubes rather than lungs, to grow to sizes that would be physically impossible under modern atmospheric conditions. We mentioned this in passing, but consider what it actually means. Dragonflies with wingspans of 70 centimeters patrolled the skies above the coal swamps. Millipede-like creatures over 2 meters long crawled through the undergrowth, and in the waters of the estuaries and shallow seas, this high-oxygen environment likely fueled equally impressive growth in marine organisms, contributing to the size and vitality of creatures like the Eurypterids and the early sharks that inhabited these coastal zones. The Tully monster, that soft-bodied enigma from the Mason Creek beds of Illinois, lived in exactly this kind of environment, a warm, brackish estuary, rich in dissolved oxygen teeming with life. The ironstone nodules that preserved it, formed when concretions of iron carbonate grew around organic material on the seafloor, encasing the bodies of dead creatures in a mineral tomb before they could decay completely. This is why the Mason Creek fossils are so exceptional. They preserve not just the hard parts, the shells and bones that survive in most fossil deposits, but also the soft tissues, the muscles, the guts, the eyes that are normally lost forever within days of death. It is because of this extraordinary preservation that we know about the Tully monster's proboscis, its eye stalks, its soft featureless body. Without the special chemistry of the Mason Creek nodules, we would never have known this creature existed at all. And that thought should give us pause. How many other Tully monsters are out there, in the fossil record waiting to be found? Or more hauntingly, how many are already lost forever there, their remains destroyed by the same geological processes that have recycled most of the Earth's crust over the past 4.5 billion years? The Mason Creek beds are a geological accident, a rare convergence of chemistry and timing that preserve things that should not have been preservable. Such accidents have happened elsewhere, at a handful of sites around the world: the Burgess Shale, the Chengjiang Biota, the Solnhofen Limestone, the Green River Formation. Each of these extraordinary windows into the past reveals a wealth of creatures that we would never have suspected existed, creatures that fill in gaps in our understanding that we did not even know were there. But these windows are rare, and they are small, and the past is very, very large. As we move through the Mesozoic seas, watching the marine reptiles rise to dominance, we witnessed one of the great themes of ocean history playing out in real time, the theme of the empty ocean. After every mass extinction, after every great dying, the sea empties. The niches that were filled by one set of creatures are suddenly vacant. And into those empty spaces, new creatures rush, evolving rapidly, diversifying wildly, filling every available role with whatever raw material evolution happens to have on hand. After the great dying at the end of the Permian, it was the reptiles that filled the empty ocean. Ichthyosaurs, plesiosaurs, nophosaurs, thalatosaurs, placodonts, a bewildering array of reptilian forms, each exploring a different way of making a living in the sea. After the end Cretaceous extinction, it was the mammals, the whales, the seals, the sea cows, each independently returning to the ocean from the land, each independently reinventing the streamlined, aquatic body plan that the reptiles had pioneered before them. This pattern, emptying and refilling, is one of the most fundamental rhythms of ocean life. The specific creatures change, but the ecological roles remain largely the same. There is always a top predator. There is always a filter feeder. There is always something lurking at the bottom, something hiding in the sediment, something drifting in the mid-water. The actors change, but the play is always the same. And so when we look at the modern ocean, we should see not just the creatures that inhabit it now, the whales and sharks and squid and fish, but also the shadows of all the creatures that inhabited it before. The modern ocean is haunted. Every ecological niche currently occupied by a living species was once occupied by something completely different, something stranger, something that would challenge our understanding of what is possible. The blue whale, the largest animal ever to live, occupies a niche that was once filled by Leedsichthys, that gentle Jurassic giant. The great white shark occupies a role that was once played by Dunkleosteus, by Kronosaurus, by Leviathan, each completely unrelated to the others, each independently arriving at the same basic answer to the question of how to be a large marine predator. The dolphins, with their streamlined bodies and their echolocation, are living echoes of the ichthyosaurs, which evolved the same solutions 150 million years earlier. The ocean is a palimpsest, a manuscript that has been written over and over and over again, each layer of text partially obscuring the one below. If you look closely enough, if you squint just right, you can still read the older writing, still see the outlines of the creatures that swam here before, still sense the deep slow rhythm of extinction and renewal that has been beating since the very first cell divided in the very first ocean, 4 billion years ago. This is what we have been listening to tonight. Not just the stories of individual creatures, strange and wonderful as they are, but the deeper story beneath them, the story of the ocean itself, endlessly creative, endlessly patient, endlessly rebuilding itself from the ruins of each successive catastrophe. And now, truly, we are nearing the end. The creatures have all been met. The eras have all been traversed. The ancient waters are beginning to grow warmer and shallower as we rise, slowly, back toward the surface, back toward the light, back toward the present day. The strange and wonderful animals of deep time are settling back into the stone. Opabinia folds its 5 eyes and drifts back into the Cambrian mud. Anomalocaris tucks its grasping arms against its body and fades into the dark. Helicoprion spirals away into the Permian abyss. Dunkleosteus sinks, its armoured head heavy, back to the floor of the Devonian Sea. The mosasaurs close their hinged jaws and dissolve into the chalk. Basilosaurus, the king lizard that was really a whale, coils its serpentine body one last time and disappears into the warm waters of the Eocene. Megalodon opens its vast mouth in one final silent yawn and sinks, slowly, majestically, back into the past. They are all gone now. The ocean is dark. The water is still. The only sound is the gentle rhythm of your own breathing, and perhaps if you listen very carefully, the slow ancient heartbeat of the sea itself, beating in the darkness as it has beaten for 4 billion years, as it will beat for billions more. The ocean remembers. The stone remembers. And now, perhaps, you will remember too. Sleep well. The strange and wonderful creatures of deep time will be here, in the fossil record, in the quiet pages of scientific journals, in the dusty drawers of museums. Whenever you wish to visit them again, they are patient. They have been waiting for millions of years. They can wait a little longer. Good night. Among all the creatures we have met tonight, there is one whose image perhaps lingers most strangely in the mind. Not because it was the largest or the most fearsome or the most bizarrely shaped, but because of what it represents about the nature of the ocean itself and the way that power manifests in the deep. We spoke earlier of the giant orthoconic nautiloids, those immense straight-shelled cephalopods that ruled the Ordovician and Silurian seas, but we moved past them quickly, and they deserve a longer moment, because the image of Camaraceras, that colossal straight-coned cephalopod hanging motionless in the water column of a 450 million year old ocean, is one of the most hauntingly beautiful and alien images in all of paleontology. Imagine standing on the floor of the Ordovician Ocean. The water above you is warm and clear, filtering pale greenish light down from a surface that is perhaps 50 meters above your head. The seafloor around you is covered in a living carpet of brachiopods, their twin shells slightly agape, filtering the water for microscopic food particles. Scattered among them are the delicate flower-like forms of crinoids, their feathery arms swaying gently in the current, and the occasional dark shape of a trilobite trundling slowly through the sediment on its many legs, its compound eyes scanning for food or danger. This is a peaceful scene, quiet, orderly. The gentle grazing world of the Ordovician benthos, the community of organisms that lives on and near the seafloor. And then a shadow falls. You look up, and hanging in the water above you, blotting out the light like a vast tapering eclipse, is the shell of Camaraceras, 10 meters long, perhaps more. A straight, gently narrowing cone of calcium carbonate, its surface smooth or lightly ribbed, divided internally into dozens of gas-filled chambers, each separated by thin walls of nacre, the same iridescent material that lines the interior of a modern nautilus shell. The shell hangs, neutrally buoyant, supported by the carefully regulated gas pressure in those internal chambers, suspended effortlessly in the water like a balloon tethered to nothing. At the wide, open end of this immense cone, the soft body of the cephalopod itself protrudes. A cluster of tentacles, perhaps 8, perhaps 10, perhaps more, we do not know the exact number, extending outward and downward like the arms of a living chandelier. Behind these tentacles, the large sharp parrot-like beak, capable of slicing through the shell of a trilobite or the flesh of a fish with equal ease, and set in the soft tissue of the head those eyes, large, complex, possibly quite sophisticated for their time, eyes that have been watching the ocean floor below, waiting for movement, waiting for the telltale ripple of a trilobite shifting in the mud or a small fish darting between the crinoid stalks. The tentacles descend, slowly, silently, like the fingers of a giant reaching down from the ceiling of the ocean. The trilobite, sensing vibration in the water, curls into a defensive ball, tucking its soft underside beneath its armoured carapace. But the tentacles are patient. They probe, they find the edge of the curled body, the beak descends, and the trilobite's defence, successful against so many other Ordovician predators, proves insufficient against this particular enemy. This is the world that the giant Orthocones inhabited, a world where the largest predator was not a fish, not a reptile, not a mammal, but a mollusk, a soft-bodied, tentacled, beak-jawed creature, housed in a shell the size of a telephone pole, drifting through the water with the unhurried confidence of something that has absolutely nothing to fear. It is a profoundly alien image. There is nothing in the modern ocean that looks like this. The closest analogue is the modern nautilus, but the nautilus is small, rarely exceeding 20 centimetres in shell diameter, and it lives in the deep ocean, far from shore, a relic of a once mighty lineage reduced to a handful of species clinging to existence in the abyss. The giant Orthocones were the opposite of relics. They were the dominant force in their ecosystem, the unchallenged rulers of an entire ocean, for tens of millions of years. Try to hold that image in your mind as you drift. A cone, 10 meters long, hanging in the warm green water, tentacles trailing downward like living ropes. The slow pulse of water through the siphuncle, adjusting buoyancy by fractions, rising or sinking a few meters with the patience of a creature that measures time in eons. The quiet click of the beak as it feeds, the soft settling of the shell as the creature drifts to a new position, effortlessly, silently, as it has drifted for millions of years, as its ancestors drifted before it, and as its descendants, the coiled ammonites and the surviving nautilus, will drift after it. This is the ocean at its most patient, its most ancient, its most serene. A world where the mightiest predator moves with the unhurried grace of a drifting cloud, and the only sound is the gentle rush of water through chambers of nacre and gas, the quiet breathing of a creature so old, so strange, and so perfectly adapted to its world that it seems less like an animal and more like a feature of the ocean itself. And perhaps that is the truest way to think about all the creatures we have met tonight. Not as monsters, not as oddities, not as evolutionary mistakes or biological experiments, but as expressions of the ocean, manifestations of the water's endless creativity, its inexhaustible appetite for novelty, its deep, slow, patient exploration of every possible way of being alive. The ocean made Opabenia with its 5 eyes, because the ocean wanted to see in every direction at once. The ocean made Dunkleosteus with its self-sharpening bone blades, because the ocean needed something that could cut through armour. The ocean made Helicoprion with its spiral saw, because the ocean found a way to build a better cephalopod slicer. The ocean made Basilosaurus with its serpentine body and its tiny vestigial legs, because the ocean was not yet finished turning a land mammal into a whale. The ocean made Megalodon with its 18-centimetre teeth and its 100,000 Newton bite, because the ocean does not do things by halves. Each creature was an answer to a question the ocean was asking, and the questions are still being asked. In the deep trenches, in the hydrothermal vents, in the cold, lightless abyssal plains, the ocean is still tinkering, still experimenting, still building strange and wonderful things out of carbon and water and the ancient, patient chemistry of life. We have been privileged tonight to eavesdrop on a few of those experiments, to peer through the windows of the fossil record and glimpse the ocean's workshop at various moments across its 4-billion-year history. The creatures we have seen are only a tiny fraction of what has been, and an even tinier fraction of what might have been. But they are enough. They are enough to remind us that the world is stranger than we know, that life is more creative than we imagine, and that the ocean, the great blue heart of our planet, beats with a rhythm older and deeper than anything we will ever fully understand. And with that thought, the last of our ancient creatures fades from view. The water grows still, the silence deepens, the strange and wonderful parade of deep-time ocean life slips back into the stone, back into the sediment, back into the patient, eternal dark. You are safe. You are warm. The ancient ocean holds you gently, as it has held all its children for billions of years. Let go now. Drift. Sleep. The ocean will be here when you wake. And perhaps when you do wake, the world will look just slightly different to you. Perhaps the next time you stand at the edge of the sea, watching the waves roll in, you will feel something you did not feel before. A sense of depth. Not the physical depth of the water stretching down into the dark below the surface, though that is profound enough, but a depth of time, a sense that the water lapping at your feet has been here, in one form or another, for 4 billion years, that it has been the home and the cradle and the grave of trillions upon trillions of living things, that beneath those waves, in the sediment that lines the ocean floor, in the limestone cliffs that were once ancient reefs, in the chalk downs that were once the shells of microscopic creatures drifting in a Cretaceous sea, the history of the entire planet is written, patient, silent, waiting to be read. The ocean does not hurry, it does not forget, it does not judge its creations, the strange ones, the failed ones, the magnificent ones, the ones that lasted for 200 million years and the ones that flickered for a moment and were gone. It simply moves on. It fills the empty spaces. It tries again, and again, and again, with infinite patience and infinite creativity, producing wonders that we are only just beginning to understand. 500 million years of ocean strangeness. 22 creatures pulled from the stone and brought back to life, however briefly, in the theatre of your imagination. And behind every one of them, 1,000 others we will never know, drifting silently in the spaces between the fossils, in the gaps in the record, in the long, dark, unwritten chapters of the story of life on Earth. This has been 3 hours of the strangest extinct sea animals ever. Thank you for spending this time with me, drifting through the ancient deep. I hope the journey was worth taking. And I hope, wherever you are, whatever time it is, that the ocean's lullaby has done its work, and that you are resting peacefully now, carried gently on the oldest current in the world. Good night.